Hello, good morning. Welcome to the second day of the Renovation Days. And today is also dedicated to the EFN conference. And just a few words who we are. EFN is a network, and mainly we are universities or research labs that deal with building facades and building envelope. And so we are for, let me check if there is the slide. Yep. You can see in this map who are the partners and the member of the network. In Italy we are Politecnico di Milano and Eurac Research. You will see then later also presentations from Eurac. And mainly we, in November 2018, we signed an agreement among us, and so from them we are working on what? Mainly we have master and program activities, we organize conferences like the one that we are now involved, and also we work with publication, dissemination of research, and also we are working with labs that test building facades mainly. One thing is quite interesting is that why we are here. After 1 year of preparation just, we are here in Base, Milano, and we work together with EDERA, and we thank again EDERA because everything that we are also presenting today is possible because they joined us and we joined them in this program. Another thing that is quite important to say is that, for example, we are really committed in building facades, and we will try today to show you what are our research outputs. And I can tell you another thing. I will be really short because we are already late, and this is quite important. We can just gain some minutes. Also, the presentation will be, there will be many presentations today, and probably there will be not so much time for questions from the audience straight after the presentation, but we have the coffee break, the lunch break, where we can share our interest, and you can ask the speaker straight during this period of time. I now give the floor to Giacomo Scrinzi and Professor Paolo Rigone, because they are here for Ordine degli Ingegneri di Milano and for UNICMI. Please.
Hello, good morning, everyone. I'm very happy to be here representing the Order of Engineers of Milano, and in particular the Energy Efficiency Commission for the Built Environment, which I'm a member of. And I also bring you the greetings of our president, Carlotta Penati, who unfortunately couldn't be here in person herself this morning. It's really a pleasure to see so many people here in this room. I think this is a clear sign of the raising interest in the matter of the designing of efficient and sustainable and technically advanced buildings, and in particular building envelopes. I'm also proud that the Order of Engineers is supporting these kind of events, because you know, the continuing education and continuing technical training for professionals is a thing. So these kind of events, I believe they're a great opportunity to exchange ideas, experiences, and knowledge between professionals and also the academic world, companies, big companies, and engineering and architecture firms. And lastly, I must say I'm also very happy to see many young professionals, young colleagues, also students, architecture and engineering students here. This is a very inspiring sign and makes to hope for the better, for the near future, and the development of new design strategies oriented to the sustainability, especially sustainability policies. So thank you very much, and I give the floor to Professor Rigone.
Thank you, thank you. Okay, today I'm here just speaking for the association, so UNICMI, one of the partners of the meeting of today. Well, I'm the technical manager of the association. So UNICMI, as you see, is an horrible name, but nevertheless it represents basically the, let's say, the Italian industry dealing with the facades, windows and doors. Well, generally we speak about metal builders, so the association includes also many other sectors, but let's say today just representing mainly facades with, of course, let's say system houses, contractors, well, the full industry. Well, of course, I'm very happy to be here today. You will see me also this afternoon. So this morning, just for my wishes for a very profitable day. Well, I also take the occasions because tomorrow morning we will have also our meeting, our European Façade Network. So that will be at UNICMI, so where we have the association. And let's say for who is going to attend to the meeting, I will send, of course, all the information about where to meet. We are a little bit worried because tomorrow we know that, of course, we are on strike in Italy. That is Friday. And therefore, but we hope that, let's say, public transportations, they will serve. So thank you again for today, and my best wishes for a profitable day. Thanks.
Thank you, Paolo. Thank you, Giacomo. So we can just now start with the first session, but before, let me just mention one, Stefano Avesani is here. I mention him because he was the one that for last November came up with this idea of joining Renovation Days with European Façade Networks, and if we are here is because also his commitment. Okay, so we can start with the first session. I leave the floor to Giacomo Scrinzi and Francesco Isaia, that are the two chairs of the session.
Hello, everyone. So let's start with the... Can you hear me? Yes. Okay, thank you. No, I just want to thank you all and introduce you to the first session. So it's going to be a couple of hours in which, the title is Industry and Innovation, Advanced Solutions for Facade Retrofitting. So it's going to be a couple of hours in which we will delve into this topic. There are going to be very interesting presenters, as you will see, from companies and not only. And without further ado, so we will leave as much time as possible to the speakers. I'm going to present the first speaker, who is Nassem Naurouzi from Arup Milano, who is going to present climate adaptation in building envelopes. So Nassem, please, whenever you're ready, the floor is yours.
Too many things in one hand. Okay, good morning, everyone. Thank you so much for being here. I'm excited to walk you through this presentation about climate adaptation in building envelope and the renovation strategies for a resilient future. This NASA map shows the global carbon sink emission balance for 2021. It's a reminder that climate system is shifting rapidly. Our atmosphere is already reacting to decades of emissions, in which case our built environment and climate is changing and evolving very fast. We've already surpassed 1.5 Celsius warming across 2024. By mid-century, even moderate emission scenarios will push us above 2 degrees Celsius. And with each degree of warming, the atmosphere holds about 7% more moisture, meaning more intense rainfall, more flooding, and more compound hazard. The EU taxonomy recognizes categories of acute and chronic hazards at the moment, including high temperature, wind, extreme storms, flooding, and landslide. And the important thing here to acknowledge is that the facade or the building envelope is the primary line of defense that has to interface with all these hazards. In the last 2 decades, we have seen about 7,000 major disasters, loss of life, and about 3 trillion global economic losses. You can see examples here from Valencia, Florida, and India, which are facing flooding, hurricane, and high heat. These are increasingly testing the performance of our buildings. And again, the building envelope is the first line of defense. Whether it's overheating, wind, flooding, or wildfire exposure, the envelope mediates that stress. It's not a single measure. It's thermal performance, solar control, green infrastructure, impact resistance, and flood resistance that should work together to create a resilience building. So as mentioned, climate risks show up in 2 forms: acute shocks and like storm, extreme winds, flooding, and wildfire exposure. On the other side, you can see, I guess the video is not running at the moment, but there's a video on the right that shows the envelope progressive collapse due to typhoon in Vietnam in 2024. And how do we manage these events and aftershocks? In the second form is chronic pressure, like ongoing heat stress and rising temperature, resulting in material fatigue and increased cooling demands, which renovations need to address both simultaneously. The dual mandate, mitigation. We keep talking about reducing carbon and improving U value, using low carbon materials and processes, and achieving net zero energy. But on the other hand, adaptation is super important as well, ensuring existing building can withstand physical stress, managing extreme heat, storm flooding, and ensuring occupant safety. The real challenge is really finding strategies that advance both goals at once. This is reconciliation that we should be really aim for. Every building starts at a different point, different location, typology, different system, different failure, and microclimate. A high-rise curtain wall will see different stresses than a precast tower or a historic masonry building. So climate adaptation is deeply context-specific and should be explored individually. So considering that, resilient renovation begins with a deep forensic diagnosis, including visual inspection, thermal imaging, and understanding current failures. Reviewing existing drawing condition and track record of repairs and ongoing issues with the building is a must-do. Calibration of existing buildings, measured consumption with energy modeling to set the existing condition baseline is super important to be able to assess those options for the upgrade. Probing material identification and understanding the as-built structural capacity of the primary structure as well as the connections for the envelope is super important. Then we have to ensure that we do carry out series of material testing to determine their structural capacity and life expectancy. Can we reconnect to that masonry wall or the brick, or do we need to penetrate through to get to the primary structure for our new connection? Can this building carry additional load? Then hydrothermal modeling. This is where we discover hidden failures like potential corrosion or condensation risk and freeze and thaw. that will lead to material deterioration once we start modifying that existing condition. Another aspect is, of course, code and standard. What are the local codes and standard? We need to establish the code baseline for the upgrade, but one of our biggest gaps right now is that the code looks backward. They reflect historic climate loads, not accelerating future ones. Just looking at EU versus US code approaches, Europe focuses strongly on policy-driven decarbonization. The US, on the other hand, focuses more on risk-driven, especially in high-hazard region. But both have a gap. Neither fully integrates future climate loads for new construction and renovations. So the performance gap here is growing, and climate risk and code requirements are diverging. We need to acknowledge that hazard intensify faster than our code currently. Buildings designed to code today may still underperform in the real condition. So what do we do to close the gap? We need to evaluate future climate loads and implement performance-based design approaches that move beyond prescriptive code paths. Another consideration is risk assessment. It helps quantify exposure, vulnerability, and consequences. So we should model how components fail under certain hazard intensities, estimate downtime, and quantify expected annual losses. This helps owners understand resilience as an investment, but not as a cost. Here are a series of climate hazard analysis that we had carried out for a healthcare client in Massachusetts for their new and existing portfolio of buildings in Boston. Sea level rise from now to 2030 to 2070 was evaluated. Then we looked at extreme rainfall and increased flood elevation by 2070. We looked at extreme heat days as we move towards 2070. By 2030, 1/3 of summer will see high heat, while by 2070, half of the summer will see high heat. And we also looked at wind intensification and how our primary structure and the cladding is impacted by that in the future. In conclusion, the future climate hazards projected for Boston in 2030 and 2070 provided a benchmark for designing a new hospital. We not only designed the hospital for this additional future load, but also as an essential facility, we ensured that it can operate in a 96-hour island mode without any external support. Overall, we can conclude that the combination of heat and flooding is now the dominant risk for many cities. So what can we do about that? In terms of envelope, we all know that improving U-value performance of the envelope is fundamental, and there are many options from double glazing to triple glazing with single low E or triple glazing with double low E to VIG and hybrid VIGs to improve the thermal performance of our envelope. We need to also consider solar protection, coating, and fritz and external shading, especially that passive strategies becoming less effective in a hotter climate these days. Air tightness is another critical issue that often is overlooked by many codes, despite having one of the greatest impact on reducing energy consumption. Impact resistance. Hurricane zones, windborne debris regions, tornado, typhoons, and flooding all expose the envelope to impact. Based on the region and climate assessment, the facade may need to be impact resistant up to a certain height. To manage impact, we typically start with the laminated glass, with SGP interlayer, reinforced framing, and then there needs to be established testing protocols. Based on FEMA, buildings in flood zones must be chosen or designed to either wet or dry floodproofing. Wet floodproofing accepts temporary water ingress in sacrificial areas, which is typically at the ground level. So the facade needs to be designed as a pressure equalized system that can allow water ingress and drainage out. And the material, of course, need to be resistant to submergence for a period of time. On the other hand, dry floodproofing systems create a continuous watertight podium where limited leakage is allowed, about 8 tablespoons per foot of facade. For dry floodproofing system, the assembly needs to be tested fully at full scales. And in the US, this is typically carried out based on FM Global requirements, which is an industry recognized insurer that also provides assembly testing. And with that, I thought maybe it would be a good idea to go through a brief case study. So I will be quickly walking you through this incredible renovation that our New York office delivered recently at the Metropolitan Museum of Arts. So it includes the skylight replacement and MEP upgrades for the ABC skylights of the Met, as you see shown up there with the red line. To give you a context, the space fully upgraded with new MEP and facade scope is located above the galleries, where it is invisible to visitors. These are the original corrugated wire mesh skylights that have been failing in the past few years, resulting in water ingress, leakage, condensation, mold growth, and overall energy loss. The convoluted mechanical space, we're reducing the amount of daylight penetration through the skylights down below to the gallery spaces. The attic was not controlled, and due to many insufficiencies, the building was consuming about 3.5 times more HVAC energy than the average museum. This is an ideal example of where adaptation and mitigation overlaps that I hinted at earlier. The project goals were set to control condensation, improve energy performance, and daylight quality, extending building service life, and provide a safer overhead glazing system, as the Met has experienced many failures in the past few years. So we started our solution with proposing a new stick frame system that was supported off of the steel frame trusses. Then the glazing system was a prefabricated cassette system for ease of installation at the steep roof. There were numerous daylight and material studies and mock-ups to achieve the level of daylight required in the galleries while responding to the needs of HVAC and lighting system. We looked at IGU versus TGU and evaluated that in relation to the mechanical system design, energy consumption, condensation performance, and capital cost, which resulted in moving forward with an IGU. The roof experienced large snowdrift. We analyzed the system for snow, wind, and access loads. Then a full-scale testing was performed to ensure long-term performance. The result was significant HVAC saving and major improvement in environmental stability and daylight performance, contributing to carbon reduction and a more resilient future for the Met. Then here are a few before and after pictures at the attic space, essentially, and some exterior images. And with that, I would like to close with our rule role and mission. So our role as facade engineers and architects, we influence both operational and embodied carbon. Low carbon materials designed for sustainability and circularity are not optional at this point. They are part of climate adaptation that we must understand and respect. And as our mission, we must translate risk for our clients, engage policymakers, embrace future data, and advance adaptive design thinking, moving beyond static solutions.
Thank you, Nassim. Very interesting framework and case study. Thank you. So I'm glad to call on the stage Kate Doherty, Fabrizia Cosimelli, Nina Glover, and Saba Maskin from WSP with their contribution about the energy and carbon performance of opaque ventilated facade. Please, the floor is yours.
Oh, right. Thank you. And okay, good morning, everyone. My name's Kate Doherty. I'm the project director on this piece of work, and I'm also the director of Net Zero and Sustainability at WSP in the UK. And look, I know, and you know, and we've just heard so much about the fact that decarbonising our buildings is one of the biggest challenges that we've got in the construction industry at the moment. And look, energy efficient retrofit, and particularly energy efficient facade retrofit, can make an enormous contribution to meeting that challenge. But there's actually a lot of unanswered questions, I think, around how specifically facades can contribute to energy efficiency in buildings. And it was at the beginning of this year that our client Trespa came to us to help answer one of these questions. And the question was, can specifically ventilated facades help reduce operational energy in buildings, in retrofits and in new builds as well? So we had a look at this and we realised that actually this is a question that hasn't been looked at in a lot of depth up until now. And if we were going to answer this question properly, we needed to put together a multidisciplinary team of experts to come together and do this piece of research. And those are the experts that you see here on the stage right now. We've got Fabrizia Cosimelli, who's our facade engineer. We've got Nina Glover, who's a specialist in computational fluid dynamics, and Saba Maskin, who's our specialist in dynamic thermal modelling. And I'm going to hand over to these three now to tell you how they came together, brought their disciplines together to do this complex piece of research and answer this previously unanswered question.
Thank you. And starting from all of this, we developed the research question asking what are the operational carbon savings of an opaque ventilated facade, or OVF, compared to an insulated rendered facade, or IRF. Our goal was to assess the operational carbon savings of opaque ventilated facades versus insulated rendered facades, and our methodology included a detailed examination of all the existing literature on the topic, together with a robust engineering assessment using CFD and dynamic simulation modeling on a real case study. And the case study featured a 7-story residential building in Valencia, Spain, and we assessed the operational carbon savings of both systems. But let me briefly explain you the differences between these two systems. The opaque ventilated facade is a multi-layered system with insulated backing wall, ventilated cavity, supporting subframe, opaque cladding, and thanks to the chimney effect, the hot air rises and exits, removing heat and moisture. The joints can be open or closed, tailored for performance and drainage. Instead, the insulated rendered facade is an external insulation system that creates a sealed, airtight envelope, reducing heat loss, and is widely used in both new builds and retrofits, especially in Mediterranean climates. For the analysis, we consider many design parameters, like climate, orientation, cavity depth, color, and so on. For the opaque ventilated facade, we analyze both open joints and closed joints, and we analyze the required build-up for the insulated rendering facade. Starting with these design parameters, this created the input for the CFD modeling, and the results were used as input for the energy modeling. With CFD modeling and energy modeling, we assessed the yearly operational and energy savings of both systems. The case study featured a 7-story building in Valencia, and we analyzed the typical facade bay, including both opaque and transparent areas, with a window-to-wall ratio of approximately 25:75. We analyzed different ventilation strategy for the typical bay, which was central to our analysis, the open joints and closed joints, which create a continuous cavity behind the panel. These configurations influence the facade behavior, so we wanted to assess them both. For the CFD model, we used the Trespa-Meteon system with invisible fixing, and all relevant components were modeled, like the backing wall, the brackets, the insulation, the air cavity, and the panel, to ensure to accurately simulate real-world performance. The analysis referenced to the Spanish standard, which set limits to the U value for residential buildings. For opaque walls in residential buildings, the limit is set to 0.56 watt per square meter Kelvin. Both the opaque ventilated facade and the insulated rendered facade were designed to meet the U value of 0.56. Both build-ups were modeled with all the required layers, like insulation, air gaps, brackets, air gaps, and so on, and their performance calculated to thermal calculation software to ensure a fair comparison of their thermal performance. So both systems can meet the same U value. All these design parameters were used to generate the CFD model, and now I will let Nina explain you this in more detail.
So to carry out this study, we used 2 types of modeling. We used computational fluid dynamics, or CFD, and energy modeling. And this slide shows how those 2 types of modeling are linked. So starting with the CFD, we looked at the wind pressures on the facade. We extracted the wind pressure coefficients and used those as input in our energy model. And that was to gain a more accurate understanding of the airflow through that ventilated facade cavity. Second type of modeling we did was to look in more detail at what was happening within the cavity itself. So we were looking at things like surface temperatures, airflow rates, and air temperatures, which we compared against the output from the energy model to understand any potential limitations with the energy model. So starting with our wind pressure model, we used a CFD software called Helix, which is a variant of OpenFOAM, to simulate the wind flow around the case study building. We included any surrounding buildings up to a distance of 500 meters to make sure we're getting an accurate wind profile at the site. We used both RANS and DES turbulence models. So the DES turbulence model gives us a very detailed picture of the turbulence within the wind flow, and we can use those results to calibrate our less detailed RANS simulations, which we run for a total of 8 wind directions. We then extracted the wind pressures on the facade and used those as inputs in our IES energy model. The next type of modeling we did was to look in more detail at the facade cavity. So this is a slightly smaller scale model. We included the case study building, some of the surrounding buildings, and we focused on one bay of that case study building, where we looked at the rain screen panels and the gap behind, and the frame support structure as well. So we ran this simulation for a single point in time, which we took to be a typical autumn afternoon. And we chose that due to the high solar radiation at that point in time. So on the right there, we can see some examples of the CFD results. And this shows a vertical cross-section through the cavity of both the air velocity and air temperature. We found that the flow within the cavity was very transient, so it's changing with time, and that the air tended to enter at the lower openings and exit via the higher openings, which resulted in the temperature profile we can see on the right, where we've got the lower ambient air entering at the bottom and temperatures increasing with height. We also looked at the surface temperatures, so this is the wall behind the rain screen panel, for both the closed joints and open joints configurations. And on the right, we've got the surface temperature of the insulated rendered facade. So comparing both the open joints and closed joints, we found the results to be fairly similar, but we did get a slight temperature drop for the open joints configuration due to the increased open area, allowing for more ventilation within the cavity. Comparing with our benchmark case of the insulated rendered facade, we can see that there's a temperature drop of around just over 5 degrees for the closed joints case and around 6.5 for the open joints. So that's due to the rain screen panels shielding that wall from the solar radiation and the heat being allowed to escape via the ventilated cavity. So we'd expect to see reduced heat flux through that external wall for our ventilated facade, which we'd expect to result in some cooling energy savings. So the next step was to quantify any potential energy savings and look at what was happening over a typical year. So that's where the energy modelling comes in, and Sabra will talk us through that now.
So for the energy modelling, we utilize the outputs from CFD, specifically the wind pressure coefficients. We integrated this in the energy modelling where we used IES-VE. In addition to this, we had conventional energy modelling inputs, which includes our external weather conditions, building fabric parameters, and internal gains. Our output is a comparative analysis of our operational energy and carbon savings through the use of opaque ventilated facade versus a traditional insulated rendered facade. We did the same comparative analysis for both open and closed joint opaque ventilated facades. In terms of our internal gains, our test case is based in Valencia, Spain. Therefore, we use the Spanish weather data file, which can be seen on the graph on the right. Spanish regulations require cooling to 23 degrees, and we can see across the year, cooling the temperature exceeds 23 degrees for quite a large portion of the time. Therefore, we have large potential to reduce cooling energy. In terms of our lighting and equipment internal gains, these were obtained from Spanish regulations and can be seen on the top right. In terms of occupancy profiles, we obtained these from a technical memorandum in the UK called TM59, which focuses on overheating within residential buildings. We created 3 energy models. From left to right, we can see an insulated rendered facade, our closed joint opaque ventilated facade, and our open joint opaque ventilated facade. Now, constructing the opaque ventilated facade was particularly challenging due to the dimensions associated with the 60mm cavity. Why is external surface temperature important? The difference in external surface temperature between our insulated rendered facade and opaque ventilated facade is what drives our energy savings. Now, this led us to the first limitation of the modelling software, and that's that the external surface temperature cannot be extracted directly. We mitigated this by calculating it offline of the modelling software. We also looked at the difference in surface temperatures between IES and CFD and found CFD had a greater temperature difference, so we investigated why. This leads us to the second limitation of IES, and that's that the heat transfer coefficient cannot be varied, and the heat transfer coefficients that are defaults in the software are very different to those obtained from CFD. What we can do is look at one point in time and compare temperatures, and this is what we did. We applied a bespoke heat transfer coefficient derived from CFD, and compared this to IES defaults and found we get double the temperature difference. What does this mean in terms of energy savings? Any energy savings that we display are actually conservative, and in reality we expect higher energy savings. There's now a video that's going to zoom into the test case, which can be seen in blue. In terms of results, we can see our opaque ventilated facade consistently performs better than our insulated rendered facade. Monthly savings of 4 to 16% are obtained. Annually, we have savings of 6%. Our peak cooling load is reduced by 5%. In terms of the energy savings between closed joints and open joints, these are minimal, and this links back to temperature difference. The temperature difference here is less than 1.2 degrees versus the temperature difference of over 5 degrees between an insulated rendered facade and an opaque ventilated facade.
Wonderful. Thank you very much, ladies. Right, so let me just reiterate some of that and conclude everything that you've just heard here today. So the research piece that these ladies have undertaken, the conclusions of that are that the ventilated facade gives us around a 5-degree reduction in surface temperature, and it's that that's able to drive the operational energy savings, particularly in cooling, which is what we looked at in this case study here. Now, those energy savings, they'll vary over the different months with different temperatures from 4 to 16 degrees, but overall we see around a 6% cooling energy saving annually. So that can be quite significant. It's important to reiterate as well as that overall annual cooling saving, we see a reduction in peak cooling load. Now, what this could potentially mean is that we could go for smaller MEP systems, and that's going to save cost, and it's also going to save embodied carbon. So some important outcomes there. Having said that, I really want to point out before I finish that this is one small puzzle piece in a much bigger puzzle. We've just looked at operational energy, and we've looked at a particular case study in a particular location, a particular typology, lots of different set variables in this research. And changing any of those variables is going to change the outcomes. So use these results with caution. We are in conversations with our client at Trespa to look at a number of potential future studies to build on this. So bringing embodied carbon into the analysis is going to be really important. Looking at different locations, different climates, implications of climate change, etc., etc. So just to point that out. So thank you very much for sticking with us through that. It was a complex piece of research, and we've been really excited to come and present it here today. Any questions? We'll all be around all day, and we'll be very happy to have a chat with you. Thank you very much. Thank you.
Aspettiamo che cambino. Thank you for these first two very interesting presentations, and now I would like to call on stage Christian de Nacard from WE Constructions, who is also partner of the INFINITE project and Horizon 2020 project that we have also recently seen yesterday afternoon. He's going to talk to us about Energiesprong for education, experience of a mix of innovation and low carbon solutions for deep renovation. Thank you. The floor is yours. Here's the pointer.
Thank you. Straight. Okay. We'll try. Okay, I'm very happy to be there. It's not too loud? Okay, it's good. I'm very happy to be there, and I appreciate to see the WSP presentation, as we work a lot with them, as we are a general contracting company worldwide, and we, let's say, participate to a lot of projects with WSP, and I'm very happy to see that they are very performing, innovative solution. And what I would like to do today is to share with you something we are very proud of. It's the first Energiesprong education project in France that we are currently delivering. It's, let's say, a very ambitious project. The idea was to share with you what we put in place for this project in order to achieve the Energiesprong performance. So I'm in charge, Christian, I'm in charge of the R&D on all the energy matter regarding buildings within Bouygues Construction Company, and in charge of several projects, internal and external, and as you know, INFINITE was part of the external project we took part. This is typical 60s construction school that we have in France. We have plenty, thousands of this type of buildings. So we have definitely a huge market to tackle with this type of construction. And the, let's say, National Education Academy required this type of new tender going and targeting zero energy building for renovation. This was not really easy to achieve because the cost matter first, and the limited time of intervention, because we have only 2 months to do the renovation works during summer period. So, what do we use to achieve this, let's say, renovation, deep renovation? First, you know, prefabricated offsite wood panel, which is something more and more common today. Anyway, this time we decided to put a very innovative insulation material, bio-based, so innovative, I call that retro innovation, meaning we are using straw, which is a byproduct from the agricultural field, and which is crushed and put within a typical wood panel facade. It is the first ever insulation material used for a public building. So we started with Activome, which is the partner who manufactured this wood panel, which is also, as a solar impulse, nice, good solution. And we not only put this new biosourced material for insulation, but we also used a quite innovative solution for windows. We have a lot of windows on the building, as you can see. And this one is, I mean, quite not so far from the WSP presentation, which is how to reduce or to increase or enhance the U value of the windows. It's a patent solution based, again, on retro innovation. You know, Pareto dynamic wall or solution is, I mean, 30 years old solution, maybe more. And a French Windows manufacturer decided to apply it on their windows. So how does it work? You have 3 glazing, which is from an energy point of view, something good. But here you have, let's say, a path of air that is normally introduced directly on the top of the windows. We call that mechanical ventilation, simple flux ventilation. And here the air is preheated in winter or pre-cooled in summer, and it increases the performance of the insulation of the window because it recovers part of the energy which is normally lost through the glass. So this is a very innovative solution put in place on a large scale. And this is really a breakthrough innovation as it is passive. There is no specific heat exchanger. And the idea is to recover not 100% like, or 90% like a double flux, but at least between 30 to 50% of energy using this Pareto dynamic solution. On the top of the envelope optimization, of course, we need to produce renewable energy on-site or off-site, depending on the possibility on the location of the project. And here, at the beginning, this school was heated with old gas boiler. And to offset this consumption, part of one of the roof was equipped with photovoltaic panel, which is, let's say, a standard solution now, even if it's not always applied on building, but it's quite common. And for this specific project, an extension of the district heating network was scheduled and normally should be connected to a substation to the district in the coming months. So, and during this time, because it takes sometimes months, sometimes years to reconnect to the district heating, a specific supply of biogas has been settled in order to use on the existing, but not for so long time, boiler gas to get some, let's say, renewable production waiting for the district heating. What is the benefit and how it is, let's say, resilient by nature? When you are using a full envelope insulation and you keep inside the concrete existing structure, then you have a benefit. You have two types of, let's say, improvement. The first is to reduce the peak load, meaning for the maximum kilowatt installed capacity of the new heating power, because you have the inertia effect, which starts to, let's say, smooth the peak temperature variation within the building. So you have a benefit on the installed capacity. The second one is that you can use this inertia during hot months, hot period, for night purging. Night purging means you open the window, either mechanically or manually, and you keep or you boost a little bit the ventilation rate. That means that during the night, you will cool down all the structure of the building, and then it helps. It's not 100%, let's say, enough, but it helps to have better internal condition and to procure resilience of the building during hot periods. On top of that, you have on each windows automatic brise soleil, which is orientable, which limits or stop all the solar load which are critical in a very hot period. As you have seen, there is a lot of glazed areas. The ratio is more 50 wall to windows ratio. and you need compulsory this type of external brise-soleil. So, having that, using, let's say, quite low-tech solution, you are able to provide a very comfortable environment to the kids, and of course to the teacher, increasing the efficiency of the education. It is clearly proved that the internal indoor air condition, temperature, humidity, noise, air quality, have a very strong impact on the capacity of the students to learn properly. That's very important for the coming generation. This is typically the installation of the prefabricated facade, wood panel module, craned, very rapidly installed, able to deliver the building in a very short time of works condition. Let's talk about figures. The total area of the building is 2,500 square meters. The wood facade is almost the same. This is a typical ratio you can have. And the total budget is 6 million euros. So per square meter seems quite expensive, but there is a lot of all internal refurbishment works. There is asbestos removal, of course. When we are doing renovation, we always face to asbestos, generally. And the target achieved is minus 60% of energy consumption, which is huge, really huge. And of course, 100% of this consumption is offset by the renewable production I showed you before. And on top of that, we decided to labelize the project. It's a new certification in France called Bâtiment Biosourcé. And there is 3 steps. And the first steps, which is already very ambitious for renovation, is how many kilo of carbon we have stored in this renovation process. Meaning that in this particular case, we stored 12 kilo of CO2 per square meter using biosource, wood material, and the like. So we are very proud of that. And the two, WeWood Le Plus Bois, is, in fact, WeWood is our internal, let's say, design solution and team and direction. And they are, let's say, designing, procuring, and challenging all the installation process of wood that could be in renovation project or new project. And they are very, let's say, pushing on how to change the rules of the, let's say, typical installer, typical supplier of wood solution, because it's a new technology. I mean, new, not that new, but from the regulation point of view, normative point of view, there is a lot of works to do for that, to increase the penetration rate of the wood facade and wood solution within the construction field. And for that, the renovation market I mentioned before is really pushing and also asking for new constraints in terms of fire resistance, mechanical resistance, seismic resistance, and a lot of tests need to be done in order to fulfill all the use case we can have Could be new construction or renovation. Some few projects we delivered already based on renovation supported by wood panel, wood solution, wood structure. And the four main topics where those solutions are very, very adapted, like extension, elevation, new construction, of course, and renovation, as I showed you just before. And a short, let's say, oh, sorry. Can you please? Yes, thanks. The last slide is really dedicated for this new, let's say, effort to be done on the wood, new solution including wood facade to be certified, and that can be used even for high-rise building. And this is, let's say, a typical test that was just done 2 weeks ago for the INFINITE project. We did with two French laboratories, CERIB and FCBA, which is dedicated for wood. CERIB is dedicated for concrete. And we would, as I mentioned previously, is our design direction for wood construction. And this is a very innovative, let's say, wood panel construction. And the cladding that you see on the picture is PV, photovoltaic, meaning this is a facade with invisible PV fixed on a wood panel solution. So the test is finished now, we passed it, and now we are quite confident to be able to deploy those solutions, very innovative, to a lot of renovation projects. Thank you very much.
Thank you. Thank you, Christian, for your really interesting presentation. And I would like to move on with calling Stefano Vesani from Ecoloop with his contribution about challenging and sustainability at product level for the building renovation.
Thank you. Good morning, all. Yeah, thank you. So, yeah, great pleasure to be here. And let me introduce. So, Stefano Vesani, Ecoloop, and I'm a co-founder and CA specialist. And yeah, since February 2024, we started with this company, and we support, let's say, industries in sustainability evaluation. The peculiarity is to merge both LCA competencies, but also, let's say, IT with an internal IT department for custom digital solutions. Let me say 2 words to thanks really colleagues from Eurac, Polytechnico, EDERA. It's such a great event and nice, really, really happy to be here for me. So let's jump into the topic. I mean, session is industry and innovation. I will try to somehow give you some direction. I think innovation for industries has to take. Actually, I think big companies, somehow front runners, can be already there. They might already have this solution, but what I want to reflect with you finally is that sustainability has some challenges which are linked to an effort, to many efforts. And then finally, I want to launch a message on a shift which is happening that will lead us all, I think, in a challenging in sustainability. So let's start with a reflection. First of all, I don't like so much the word sustainability today because many of us, let's say like this, around the world, we use it in a very broad and not so specific term. And so, as you see in the graph, I mean, many aspects, right, are involved behind sustainability. So saying specifically product sustainability, and I will try to give an example also for the, let's say, renovation of buildings, might be a bit saying nothing. So one of the aim we have as Ecoloop is trying to build some practical evidence, practical, let's say, meanings of sustainability. What is then behind all this? Then finally it's a matter of data. This is really, I think, the fil rouge of my presentation. We have worked since many years in sustainability in general, right? But now it's really the time to build a real meaning on sustainability for products based on high quality data. You might know, I will say 2 words about this, that to bring, let's say, some evidence, you need to make calculations. And as every model, garbage in, garbage out, right? So you have to provide good data. And this, let's say, will support the kind of sustainability statement you want to do. And so key point is to start to talk about data. And what I like is the fact that in buildings, and I used to work a lot with facade in my previous life, and so facade as assemblies are made of components and then down to materials, right? So if you see these bubbles, one inside the other, you can think about how to make an assessment of a renovation of a building in terms of whole life carbon, or to support a certification for green labeling. Then you need to go down and to ask your supply chain to provide you data. So the chain of data is what is needed now. I will try to make an example about, let's say, focus of something we are developing in the field of life cycle assessment and EPD. So the market, I didn't put a graph. I used to do a lot of presentation with graphs. Now I'm more in a marketing style, but I think you can pick up the message. So the level of number of EPD, so environmental product declaration, published in different program operators in Europe is really exponentially growing. That's good. And what's behind DPD? So DPD is finally a dress code of a life cycle assessment study, okay, specific for a product. So in this field, let's change the slide. Again, we are asking, so the real challenge, I think, of the first point of the agenda is really to think how we can provide this data, and this asks company to open their databases, their management system. We tend to work also with very little companies which sometimes do not have. So you need to talk to suppliers, asking, again, to supply data related to the products you buy from them, and also databases, right? So general data of emission factors versus specific primary data also in terms of emission. So finally, for companies, what does it mean? It means a great big effort. Of course, now I will stay quite high. I say always to companies, yes, you have to put an effort, you need a consultant, you need to provide data, and you need your employees to study all your data, but there is a value, of course, that you are selling for your company, for your product, and as in this picture of the chain of data, you are somehow supporting sustainability, let's say building reliable data worldwide. So why we need this effort? Because, okay, first of all, we have seen a lot of optimization pathways that can start inside the company if you are able to study your own production, your own data, your own supplier chain, also in terms of sustainability, but first of all, you need production data. So second, of course, is marketing somehow, and start to build a competitive value for your product if you add on beside the normal requirements, also the topic of, for example, EPD or life cycle assessment impact data. And finally, the topic of norm compliance. I would say that might be a bit of matter of discussion, but finally the direction is very clear, right? Now there is the new construction product regulation enforced and active from 8 January 2026. And so all new products that will be with CE marking then will need this, okay, this kind of data. Now I think the best slide I have. Let's go a bit now into practice, because then leads me to, let's say, the core reflection. So when we talk to a client about making a kind of analysis as the one I'm telling you, basically there is 3 answers. Yes, of course, I believe in sustainability, I want to do it, we have the best eco product, green, whatever. Great, okay, we can do it. Then second, yeah, okay, we can do it. Finally, this is marketing and communication budget, talk to my colleague, but something we can do. And then finally, okay, I really don't like this. Am I obliged to do it? Okay, then I will do it. That's clear, because as I told you, this is an effort, and this bring value that, yeah, we are building this value a bit together somehow. So in Ecoloop, we are thinking about, yeah, this is me popping out from a nice tool. So basically, it's true, again, there is an effort, but you can reduce this effort and this cost. You can assure data quality and improve your product specificity and competitiveness. And the idea is to basically develop custom tools, custom algorithm for your company that you, let's say, you can couple that with your management system. And this especially for products, and I've done a little example for prefabricated facade, is able to, let's say, transfer in a very, let's say, simple way, a kind of bill of materials for all what is raw materials, then automatic calculation on transport with your own database of suppliers, and then coupling this with your production line performances, so let's say waste, energy, and so on. And from this, of course, let's say real-time calculation of the impacts. That's an example of climate change, potential indicator, and of course, all the list of the needed indicator. Of course, finally, what's behind here is also the topic of EPD generation. And fortunately, there is a kind of challenge on the market between program operators, which are the entity which delivers, let's say, and publish the environmental product declaration, the EPD. And there is the possibility to certify for your company this tool and, let's say, create, let's call it a machine to publish EPD in a quicker way, but again, assuring data quality and reduction on cost. So I wanted to end with this, let's say, switch of words. Until now, you need probably the EPD, you need the data, and almost nobody really read it. Nobody understands even sometimes the number of, the quantity of numbers that are inside, right? So, do you have the EPD? Do you have a carbon footprint of your product? Good, give me, let's go on, we will do this project. But that's today. I think if we manage to exploit digitalization, we can assure this high quality data flow and, let's say, strengthen the data chain, right? And this then will lead us to challenge in sustainability. So finally, you as a supplier of a product, of a material, of an assembly, of a whatever, will be asked, how good are you in this indicator? For example, okay, global warming potential, but there are many others, right? And that might be, I think, compare against competitors. And if you are relying on general data, you will lose, because, let's say, database data are really overestimating the real let's say, impacts, right? So I think this switch between, okay, sustainability is a burden, has many challenges inside, actually lead us to this switch, which is really needed and can really create for your company, let's say, a competitive value, let's say. And I will not talk if you believe in sustainability, we can talk in lunchtime. But finally, there will be a winner. There will be not anymore, I have the certificate, so I'm in, I can be your supplier. That's more or less is all what I wanted to pass. So I think this is the vision, and the vision is quite approaching quickly. So data is the key. So your own data has to be reliable, but collected in a smart way, and usable somehow for all you need also for this kind of sustainability evaluation, and can highlight the value of your product finally. Optimization with this tool idea, I think, is possible, and yeah, I think it's really a direction that also, let's say, many big companies has already taken, and we can work on this. So, thank you. It was a pleasure to be here, and hear you later.
Thank you, Stefano. Now, we changed a little bit the topic, and it was really interesting to see the role of data, and I mean, it's a bit broader, but very also in line with what we have seen in these days regarding facades, and industrialization is becoming more important in all fields. With our next presenter, which is Alessandra Navarro from TU Delft, we're going to talk about another topic, it's a different one, on the Open Face program, which is an education program, and Alessandra will talk to you about it. Thank you.
Thank you. Good morning. I think in this room we are all aware that facades are extremely important. I think we are a bit all facade geeks here. But high-performance facades that can actually tackle climate and material crises require knowledge and expertise. But not everyone in the world has access to this knowledge. How many universities do you know that are actually offering facade engineering education? How many companies do you know that specialize in high-performance facades? This was the challenge that we wanted to tackle together with Eurac and TU Darmstadt to offer open, free, worldwide accessible education on facade design engineering. There is many countries, many universities, many companies that would do with some additional new free material on many topics of facades. In Open Face, we go from what is a detail, how to detail, up to circularity, climate resilience. Of course, we try to find a style that is up to date with the media and the social media we are used to, so we try to do it in a fun way. But Open Face is made of many types of educational material. So in particular, we have structured the content in 7 systematic courses that we're going to have a look in a moment together, but that together you can take and also earn a MicroMaster, but also, and much more interesting, I think, for the audience here, all the material behind Open Face, which is videos, handouts, exercise, is easy, free, open to use for all of you in a plug-and-play mode. So if you have a course or you want to use one of these materials, you can just take what you need. If you are in a company where you offer training and you would like to use some circularity, update material, or climate resilience, this is all for you, open and accessible. And this is thanks to a very interdisciplinary team that I would like to present now. So I'm Alessandra, as Francesco said, I'm from TU Delft. I'm together here with other colleagues from TU Delft, Marcel Bilo, but also this is a core program with our colleagues from Eurac. You may recognize many faces in the audience today here, and TU Darmstadt. So here we have an interdisciplinary team. We go from building physics to structural design, circularity, climate resilience, how to detail and construct, but also many of our educational content was based thanks to our collaboration with the European Façade Networks, and I will show you soon some snapshots. This is the idea of offering open, free education didn't start in one day. You can imagine the effort behind providing such high-level quantity of content in a free and open access way. We started in 2020 where Ulrich Knack and Marcel Billo took a camper van and went around Europe interviewing experts on facades, and they created the first online video material, which was an introduction to facade design. And what we saw is that it was highly successful. We had a lot of learners. It is also true that this coincides perfectly with COVID. This is also true. But of course, this marked a shift in the way we train and we get educated on updated content. Then we were successful in obtaining Erasmus Plus funding, and this is why the three of us as partners are able to offer this content for free. I'm going to walk you through the 7 systematic courses that we are now offering in terms of content and material. We have an introduction to facades, as I said before. Then we move to principles, materials, and technologies of facade, and this is about learning what are the facade typologies, what is a facade, all the basics information on envelope. Then we have 2 courses on learning how to detail, and we go to the detail here, to detailing design and construction requirements. And there are 2 systems we tackle, stick systems and ventilated facade. And then we have a series of more advanced topics. We have theory and technology 2, which is the performance-based facade design. So here we go and we learn about how to assess structural performance of facades, building physics, fire, and acoustics, and so on. And then there are a couple of courses that are more novel. One is related to circularity principles for facade engineering, and the last one is called Facade Forward, and it's about the process of innovation in the facade industry. I would like you now to walk you through one of these courses to give you an idea of what does it mean to take one of these courses. This is, for instance, how to detail stick systems. We start from learning with experts, worldwide experts. We start learning what is a detail. Then we look at different materials, aluminum, steel, wood. Then we go through different aspects of the detail, up to knowledge of how to detail difficult parts of a facade, such as window connections, doors, top-level facades. And then there is a final module about meeting experts to assess your detail in terms of fire, building physics, and finally, tender process, contractor and shop drawings, and problem and challenges on site. This is an example of a course. As you can see, is 6 modules. So in 5 to 6 weeks, you can take it online in edX, open access. And as I said, any of the material here can be used plug and play in an existing course. It's not just a bunch of videos. Here, what we also looked at was to provide active learning. There are a series of live webinars where we meet students worldwide and we answer questions. This is an example of last week where we were looking together at questions on deflections on mullions, which is also important. Also, we share examples with students. They bring their examples and we have live discussions. We have also prepared a number of assignments that are open access and they're used within these courses to do peer-to-peer learning. So there is a forum, students post their answers, it's in a safe environment, we monitor the responses and we give feedback. And these are other examples of these assignments. And then I think we can find here a bit of everything for everyone because, as I said, we go from the basics to more advanced topics. In fact, we have done several visits to partner institutions. Here we are at Polytechnic of Milano, where we were looking at ventilated facade detailing, for building physics assessment. These are footage where we look at cutting-edge testing facilities. Here we are at Eurac, where we are looking at how advanced facade components are tested in realistic environments, and we can, and therefore, show this worldwide to show to students or architects and engineers in the world how would you assess high-performance facade. And this is another example of visits to Polytechnic of Torino, where we looked at advanced facilities and knowledge on solar control in facade technologies. So there is a very high variety of content for any type of topic holistically around facades. All of this is available in our website, openface.world. And this is the website where you can find all the online resources, and we post also information on events. These structured courses I show you are in edX. I would like also to say that if you take all the 7 MOOCs, you can get a MicroMaster certificate from Delft, and this is equivalent to 15 ECTS. So also for the, a remark to say that, of course, this cannot fill in all the knowledge that you need to become a facade design engineer. Is a basic. We are trying to give an introduction, a basic worldwide on facade design. So this doesn't substitute live programs where you can do one-to-one learning in our universities, but it's more a call to share together educational material, make it available worldwide. So if you're also involved in facade education and you would like to contribute with your material, feel free to reach us, because the more we are and the more we share our knowledge open and worldwide, the higher is going to be the impact. And I'll leave you with our last trailer, just to leave you with a laugh. We try also to be as funny as possible in this MOOC. This is our trailer for performance-based design. We show from building physics to structure, but we try to also provide some trailers
performance-based design of facades is a serious business.
In my lab. I don't
if you want to know
what's
going on here, don't waste more time.
Stories for the
Just enroll.
How we get to this story. So thank you very much. This is the QR link. Let me know if you have any questions.
Thank you, Alessandra. Thank you. Very inspiring and important initiative. So congratulations. And last but not least, I want to call on the stage Mauro Tricotti from Rockwool. Rockwool is a gold partner of this event and is sponsoring this session. So please, Mauro, the floor is yours.
Thank you. Good morning. I'm not so easy to speak in English, so I prefer, if I can use the Italian language, because I want to share our experience in a very interesting project, but the technical details I prefer to explain in Italian. Chi siamo? Produciamo lana di roccia e la cerchiamo di usare per tante applicazioni che abbiamo concentrato un po' in questo progetto che adesso vi racconto e che ha visto l'applicazione di un concetto di facciata che andava appunto a rispondere a tante esigenze, quindi a ingegnerizzare il concetto di facciata non solo per migliorare l'aspetto architettonico e prestazionale in termini di efficientamento energetico, ma anche per includere delle tecnologie innovative in termini impiantistici, quindi usare questa soluzione per rigenerare in maniera completa l'edificio. Siamo in provincia di Cremona, si tratta di una struttura per la cura di pazienti anziani, quindi una RSA. L'obiettivo era quello insomma di rigenerare e quindi ridurre gli impatti energetici dell'edificio, ma operare anche sotto il profilo di migliorarne la qualità. In termini di sicurezza stiamo parlando magari anche di aspetti che in Italia coinvolgono l'aspetto di miglioramento sismico e quello di garantire comunque livelli di sicurezza. Siamo in una struttura ovviamente con persone che hanno problematiche in caso di evacuazione, quindi in caso di incendio, quindi che avevano l'attenzione particolare anche in termini di sicurezza su quell'aspetto. Queste è alcune immagini dell'edificio come si trovava prima dell'intervento. Ovviamente stiamo parlando di un edificio con gravi problematiche anche qualitative, architettoniche, quindi che necessitava in ogni caso di un intervento di riqualificazione. La scelta appunto della committenza e quindi poi con l'apporto della progettazione era quello di sfruttare al massimo l'opportunità dell'intervento per migliorare in maniera significativa le qualità di questo edificio. Quindi questi erano gli obiettivi che con la committenza e quindi poi in collaborazione con la progettazione siamo andati ad analizzare, quindi migliorare, come vi dicevo, l'aspetto sismico, c'era questo obbligo e quindi era fondamentale. Efficientare e quindi spingere il più possibile l'efficientamento energetico, anche perché i costi di gestione di questo edificio erano molto importanti, migliorarne il comfort, immaginate appunto siamo in un contesto dove l'aspetto invernale era un tema da affrontare, ma c'era anche il problema estivo che sta diventando sempre più evidente, quindi l'idea anche di migliorarne il comfort estivo. Sicurezza incendio era un obbligo, ma era anche un'attenzione che la committenza ha messo come una delle condizioni vincolanti, e gli ultimi due erano sicuramente un po' più sfidanti, che erano sicuramente rispetto dell'aspetto economico, quindi c'erano l'opportunità del bonus 110 e quindi cercare di sviluppare una progettazione che andava in quella direzione, ma anche ridurre al minimo l'impatto del cantiere e quindi trovare una soluzione di intervento che riducesse il fastidio e che fosse anche possibilmente molto rapida, proprio per ridurre veramente questo aspetto di disturbo che si poteva generare con un cantiere di questo tipo, così importante, che vedeva un intervento così drastico. Qui la sfida è stata appunto con la progettazione, che ovviamente ha portato a tempi di sviluppo dell'idea e quindi delle soluzioni impegnative. Non si è trovato una soluzione standard che poteva essere quella di un intervento più tradizionale che abbiamo visto anche citare oggi, quello di un sistema a cappotto, realizzando quindi un intervento consueto, ormai applicato in maniera diffusa sul mercato. L'idea era proprio di trovare qualcosa che riuscisse a coniugare tutte le esigenze prestazionali che si volevano ottenere e garantire però questo aspetto anche di riduzione degli impatti, e qui si è cercato, quindi qua il contributo che poi abbiamo dato anche noi, di portare avanti un'idea che andasse in questa direzione, quindi il tema della prefabbricazione, che quindi si sposa anche un po' con l'approccio di Energiesprong, e quindi creare una struttura, una facciata che poteva rispondere il più possibile a queste esigenze. Quindi la parte di progettazione è stata veramente impegnativa, nel senso che si è dedicato più tempo alla progettazione che alla realizzazione stessa, proprio perché c'era la necessità di intervenire in maniera efficace, efficiente e riducendo al minimo quelli che potevano essere inconvenienti tipici di una cantierizzazione. Quindi quello che si è operato è, come vi dicevo, una soluzione prefabbricata, quindi con pannelli sandwich, in questo caso la collaborazione con Isopan è stata strategica, garantire poi quindi con un intervento anche di elementi strutturali in acciaio l'adeguamento sismico e sviluppare un'idea con la parte di impiantistica che prevedeva appunto la sostituzione integrale degli impianti preesistenti e portare la parte di distribuzione dell'impianto all'esterno, quindi sfruttando la facciata per ridurre, come dicevamo all'inizio, quella problematica di impatto che poteva avere sull'utenza. Quindi gli interventi sono partiti prima con ovviamente l'identificazione delle soluzioni e quindi l'installazione poi dei sistemi di miglioramento sismico, quindi queste strutture fatte da mani SIPREM, che andavano quindi a creare un esoscheletro per ridurre quelle che erano le problematiche preesistenti di un edificio realizzato in più anni, con più ampliamenti, e che quindi aveva problematiche abbastanza evidenti. A questo punto si è operato nel isolare l'edificio, quindi si è sfruttato sia il riempimento, quindi con lana di roccia a riempire quelli che erano gli intercapedini che si sono generate con l'inserimento di questa struttura di esoscheletro, e con pannelli sandwich che quindi sempre isolati in lana di roccia andavano a creare questo rivestimento isolante che andava quindi ad avvolgere il nostro edificio. L'intervento poi ha previsto anche nella copertura, non ho le immagini, mi sono concentrato sul tema della facciata, ma anche lì con la tecnologia di pannelli sandwich sempre in lana di roccia per sostituire l'esistente e quindi andare comunque a generare in maniera molto rapida un intervento di recupero. Quello che si è fatto quindi poi è ovviamente ricostruire anche un aspetto architettonico a questo edificio e quindi anche un'immagine, e quindi con un sistema AdWin sviluppato da Isopan nel creare quindi una pelle esterna che veniva vincolata al sistema di facciata e di pannelli sandwich con un sistema brevettato da loro di ancoraggi che prevede quindi la creazione di un'orditura su cui andare a fissare il cladding finale. Come vedete qui anche per il tema della sicurezza antincendio si è lavorato con il progettista antincendio nel controllare poi quelli che potevano essere le criticità che in una facciata ventilata vanno considerate, quindi gli elementi di protezione intorno ai serramenti per evitare che un incendio che si dovesse generare all'interno dell'edificio potesse trovare nella facciata un elemento di propagazione. Considerate che è un edificio di 3 piani e ogni piano è considerato un compartimento, quindi doveva garantire una compartimentazione tra un piano e l'altro, quindi per evitare che il rischio incendio potesse muoversi all'interno dell'edificio tra un piano e quello superiore. Qui vedete già una prima immagine, vedete degli elementi, sono quel far barrier, quegli elementi bianchi che sono sempre pannelli di nostra produzione che hanno questa funzione di, nella facciata ventilata, intervenire e bloccare l'eventuale propagazione di un incendio, poi li vedremo meglio analizzati. Qui vedete appunto l'applicazione della parte impiantistica, quindi la sostituzione di un generatore tradizionale con pompe di calore che venivano posizionate all'esterno e con fan coil all'interno, quindi a sostituzione dei radiatori, che hanno però portato la distribuzione attraverso la facciata. Questo tema è stato curato anche sotto il profilo però della sicurezza antincendio. Lo vedete in alto a sinistra, ci sono quel percorso orizzontale della parte impiantistica che per sicurezza è stato protetto con questi sistemi di far barrier attivi, quindi pannello in lana di roccia con un elemento intumescente che in caso di incendio si attivano e vanno quindi a bloccare l'eventuale propagazione dell'incendio lungo la facciata. Qui vedete appunto, come vi dicevo, il tema dei far barrier, lo vediamo in maniera un po' più chiara, e questo era fondamentale visto che il requisito di sicurezza antincendio era vincolante, era cogente, ma era anche, come vi ho sottolineato, un aspetto su cui la committenza era molto sensibile. La finitura è stata fatta sempre con pannelli in lana di roccia, in questo caso è un cladding, una matrice quindi lana di roccia verniciata, sempre un nostro prodotto, e anche qui l'idea era quella di dare un'immagine qualitativa che garantisse una durabilità all'intervento e che rispondesse poi anche ad aspetti estetici che erano quelli che poi in questo caso il progettista architettonico ha cercato e quindi con noi ha cercato le soluzioni per rispondere anche delle immagini che davano una modernità all'edificio che ovviamente non aveva preesistente, non aveva una qualità. Qui vedete alcune immagini, l'intervento considerate ha coinvolto circa 9.000 metri di facciate, l'intervento ha avuto una durata complessiva di meno di un anno, quindi un intervento molto rapido, ovviamente fatto a lotti per cercare appunto di ridurre l'impatto, ma come vi dicevo è stato un intervento estremamente importante. L'aspetto importante e significativo che abbiamo già registrato è stato appena completato questo intervento, che nel periodo estivo in cui stavano intervenendo sulla parte impiantistica, comunque la mancanza della parte impiantistica che doveva comunque garantire il comfort nel periodo estivo non ha portato particolari fastidi, visto che comunque i livelli di isolamento che erano stati già inseriti hanno garantito un buon comfort e quindi, tornando anche alle presentazioni che abbiamo visto oggi, sicuramente nel periodo estivo il sistema della facciata ventilata ha contribuito in maniera significativa a ridurre gli apporti e quindi anche il discomfort, in questo caso appunto in questo tipo di applicazioni. Ovviamente si è lavorato anche, come vi dicevo, sotto il profilo architettonico, cercando di studiare sempre con la stessa matrice, quindi con i pannelli rock panel, nel creare anche degli schermi, quindi degli elementi di ombreggiamento che andavano quindi a proteggere le zone, queste frontali che sono legate agli uffici, per anche controllare quelli che erano i rapporti gratuiti estivi dell'illuminazione. Questo intervento quindi è un intervento secondo noi molto importante perché ha visto il coniugare in un intervento di facciata tutta una serie di esigenze e di problematiche che sono state risolte ovviamente con un'attenta progettazione, una scelta di dettagli e di soluzioni studiate a priori, quindi cercando quindi di prevenire tutte quelle che potevano essere le problematiche di un cantiere che con questo tipo di tecnologie diventava complicato poi realizzare. E la cosa interessante appunto è stata che anche sui tempi di realizzazione che erano stati previsti si è anticipato in maniera drastica il termine dei lavori grazie appunto a una facilità, una capacità di aver progettato in maniera puntuale tutti gli elementi e quindi riuscire a non avere problematiche che rallentassero il completamento del cantiere. Io ho finito.
Okay, thank you. Thank you to all of our speakers. So this actually closed our session. And I mean, incredibly, we are not only on time, but we are 15 minutes early. So in my opinion, it would be also an occasion to open the microphones to the public if you have questions to any of the presenters that you have heard so far. So if you want, we can do that since we have a little bit of time before the coffee break. Are there any questions from the audience? Shy people, or no one is raising their hands? I mean, I don't know, I have some curiosities, but I don't know if we want to go directly to coffee break and do it on...
Go, Francesco.
Okay. No, I mean, I've heard a lot of interesting topics today, so maybe one thing which I would like to ask to our first speaker, who talked about, you talked about like two trigger, let's say, key words that I've heard were about resilience and so building envelope resilience to climate change, and also very impacting and let's say phenomena which are getting higher and higher frequent with higher and higher frequency, like very heavy storms or heat waves or stuff like that. And you also talked about the performance gap, which are two different things, but I mean, it's also very important. Then, I mean, another trigger word for me was Stefano Vesani's presentation on data. He talked about data on a different level, but I thought, what do you think is the role of data, even maybe real-time data on buildings, to be able to prevent or to act against these very, very like striking and very bad phenomena that are, let's say, striking our buildings?
Well, I think you can look at it in, again, two different things. Data in terms of EPDs and sustainability compared to data for climate, right? How you're using existing, because basically all the climate data that we have is from up to, like from the past to recent, and then we are just accumulating more data day to day, right? Then the question is, how are you interpolating that change and reflect that to the future to make some assumption on where you're going by 2070 or 2090, right? And designing to that. So that's a completely different data. Then the EPDs, that's something else that we are dealing with, and I've been exposed to it a lot in the US, because the US is a little bit different than in Europe. We are not pushing for EPDs as much. So in our practice, from our office specifically, what we are doing with EPDs and trying to gather information about material sustainability is from us, the designers, including it in our specification as a requirement. So the contractor now is obliged to provide us with that data. Then that is helping us with creation of our own internal data in terms of material sustainability to create this platform that can be used, because there's that lack of data. So there's two different data to talk about and think about, I guess.
No, thank you. And actually, I would introduce maybe a third data, which I was also thinking about, which is, so to summarize, maybe we also with Stefano, we talked about data which are, let's say, intrinsic on the material, on the construction. Then there is the data which is related maybe to weather data, which we need to use maybe more updated and even looking forward weather data. And the third level, which I was also thinking about, is real-time data on what's going on in our surroundings, in our environment, and inside buildings. So to be able to react to what's going to happen in the near future.
That's also super important. So what we're doing with some of our existing building, trying to implement sensors within the wall to understand how it's performing over time, because I know that Rockwell showed insulation on the outside. I don't know if I agree with that quite, because I think it's more complex than just covering a building with a blanket. So I think it's super important for existing building to understand how we are changing them with our additions, external, internal, how that's gonna change their resiliency throughout time, because these are buildings that they have been exposed to rainwater and water ingress for so many years, and we are changing, shifting that performance. We are changing the dew point location, right? How is that impacting the long-term service life of that material now that we are changing the dew point? We are pushing it a little bit more probably inside. For example, if you're dealing with a masonry building where you have 3 whites of brick, always on the outside you have this more like a stronger, longer fired brick on the exterior, and then you have more porous, poor sort of fired brick on the inside. And now that you're changing that dew point, how your inner whites of brick are going to react. So it's interesting to, I think, include sensors within the cavity of the wall to understand how we are shifting the change within the wall buildup as we are modifying it. So it's super important, I think, to do the analysis to understand where we are going with the change. Yeah.
Thank you for your answer. And if also other speakers from the session want to build on that, feel free to do that. Otherwise, let me ask again if the audience has some questions, maybe triggered by this answer. No, I don't see any questions. So I still have a lot of curiosities to ask to other speakers, but I would say that I would take a longer coffee break, or so that we can start a little bit earlier, so we don't fall behind like we did a little bit yesterday. And we will continue our discussion in the coffee break. So thank you all, and with this we close this session.
And see you again 11:45.
speakers will be so effective to stick on the time, even if they have a few minutes less. So I'm the moderator of the session together with Sofia. My name is Roberto Lollini from Eurac Research, already mentioned it several times. I'm very happy to be here. We have a great session in front of us and quite challenging how to move from research to practices. So, I mean, we have a lot of very interesting presentation. Sofia, if you want to introduce yourself.
I'm Sofia Pastori from Politecnico di Milano. I am a research fellow, and yes, I think that we can start with the first speaker.
Super. So, I would like to get the floor to Taleia Costantino from TU Delft, professor there and expert in facade since many, many years. So, the floor is yours.
This one, yes. Hi, everybody. I'm very happy to be here, not only as an EFN member, so because that's also an EFN conference, but also because INFINITE were in the same innovation cluster on industrialized renovation. So I'm very happy that I can be there, and I hope my voice stays with me for the coming 13 minutes. So I'm going to talk about scalable renovation. So we are all here very interested about renovation, and I want to share some insights that we have from different research projects about how we can scale up. I was warned that this is hard to change. Okay. Yeah, no. The previous session was much better. Okay, yes. So, of course, like our starting point is the decarbonization. We have to switch from fossil fuels and be carbon-free. That's what we want. That's not only for the built environment, that's overall. But, of course, existing buildings have a big role to play there. So now it goes too fast. So, and we know that both the rates and the depth of renovation needs to increase. This is a study that was done more than 10 years ago now, like 14 years ago, and it projects that in order to reach these decarbonization goals, we need to go from minor renovation with little savings to deep renovation towards zero energy renovation. However, we all know already that this is not what has happened, and the renovation rates, particularly focusing on deep renovation, are very, very little. This is from the renovation wave document of EU in 2020. In the same document, it says that deep renovation needs to happen in more than 35 million buildings by 2030. So I did some math there, and this means that's how much we need to renovate per day on a European level. I think it's clear that we cannot do that in the current practices and with the current labor shortage and material and so on. So industrialized renovation could be an effective way to go, and you have seen, I think, especially yesterday, a lot of things about that. It can improve productivity, it can improve the cost through economy of scale, reduce on-site construction so we can do more buildings, and have efficiency in the design and engineering, so it becomes more of a repetitive, and also reduce waste. So how I see we need to define industrialized renovation is a renovation that increases energy efficiency, incorporates renewable energy to reach this deep renovation level that we want, maximize reproduction because we have to do so many. Of course, building and existing buildings are different, but a lot of things do not have to start from scratch. And it should have a large amount of prefabrication and modularity in the concepts to be able to do that. So this is ENSRE. That's a European project that started with the objective that I explained. So there we designed a prefabricated renovation. We had the idea of have this mesh that different constructions are possible. That's a project that was running in parallel with INFINITE. There were sister projects, so it also finished a few months ago. And we did develop the technical solution. So we see here we have a standard mesh, and then different options for facade are possible. So here are for the opaque components. The window can be prefabricated. And here we have different active components, which that's a standard process of development. We had to test it for fire and so on. We did install it in a pilot, in few pilots. Actually, this one is the one in Estonia. But apart from the actual technical solution, another thing we realized, which links to what I was saying about the design efficiency, is also how can we have more automation in the process, and then we also developed a digital platform that can do that. So it's not only the prefabrication of the component, but it's also the automation of the design process. And that's another European project, again, try to achieve prefabrication. And you see here some different modules based on the same principal idea. This is because adaptation is a very big part. As we all know, it's not that we want the whole built environment to look the same. So having solutions that have possibilities to adapt to the specific needs of the building is important. Here, our part was really to think of how we can make these solutions that we have seen also in other projects that are possible. How can we make them more circular? And we started by defining key performance indicators. Stefan also mentioned some in his talk. Global warming potential, of course, is an important one, but also recycled content, how much of that is coming from renewable sources, and so on. And with that in mind, we have to understand, again, this is very similar with what Stefano showed, so I'm happy that he had this introduction, because we need to think of the facade in levels. And then we can identify the facade as an assembly, but of course it consists of components and material. And it's not only about what we assess, but also to what level do we make the design decisions. And in that case, that's the basic concept of EGIR. And for the different components that make up the assembly, we have different performance indicator that we wanted to prioritize. For example, window is more about durability, insulation is more about where the material is coming from, and so on. Of course, we did do some more analysis, material flow analysis, because we need to understand where the material is coming from, if we as product developers are trying to improve it. And we also tried to benchmark, so we did look at the EPDs, and then make a benchmark for similar projects, what would be the carbon footprint, but also the recycled content. And because I do agree with what Stefano is saying, that we do need to select the best product, and that's things that we need to have in mind. So to upscale the renovation, I highlight some things like it's about technology integration, cost effectiveness, industrialization, but also circularity. But if we talk about upscaling, we have to look at the district, we have to look at the city, and what is this interaction? And then we go towards the positive energy district idea. So energy districts, I have some definitions there, are some concepts that are promoted by European Union and other initiatives. I'm not going to read them through, but basically it's about energy efficiency, energy flexibility, and energy generation, but on the larger scale. In the end, it's not only about decarbonizing one building, because the building does not work in isolation. We need to decarbonize the whole system. And there are challenges there. Governance is one, but also social integration and so on, the incentives to do so. Of course, we also have challenges like balancing the energy and the demand. And this is where I want to link to another project that we are working on, because energy transition is a challenge because we have two domains, built environment and energy systems, that work in isolation. So this is a graph, this is coming, it's the incentive from the Netherlands, but it's the climate agreement of the Netherlands, but we have similar in other countries in the EU level. We both need to reach decarbonization, but we don't necessarily talk to each other. So we have the built environment when we make decisions to renovate the building, we have to know what energy system we're going to have, but we don't necessarily have the view how it can influence the city. On the other hand, energy infrastructure looks at the building in an aggregated way as a single node and doesn't have a long-term planning. So in our project, we want to use digitalization and a digital twin to kind of bridge this gap and help in this strategic planning. Because we see the microgrid involve many different aspects, and the building is one, but normally it's like a static model, while we have been talking now how it needs to improve efficiency, but also how we need to transition from fossil fuels, and this means maybe using more heat pumps. That's something that we do a lot. This will completely change the electricity consumption and layout. So combining those is very essential. I'm not going to go, so we did develop a digital twin to do urban building energy modeling, which has automated pipeline, work with archetypes, and has the chance to harmonize the data infrastructure. I'm a little bit rushed by the time, so that's why you see me looking at the clock. So this is a little bit how it looks like. I cannot go into too much detail. It's also a very complex system because it's about big data. So, but it's really about how can we go towards having information for district, for larger scale, because this is also how they can connect to the buildings. Energy infrastructure and all the results that we have grid conjunction and so on, do not change from one building, but do change from the bigger system. So in our case, you can select an area based on archetypes, select the buildings, and we have some definitions, and in the end, you can get aggregated results of the performance of this area. And at the same time, we also have the chance to compare variants for interventions. So with this kind of tool, we can achieve both short-term and long-term optimization in the sense like we can, in the short term, better manage the demand and supply and also support the grid operator to identify and cluster and identify the demand patterns. And our goal here is that we aim to support non-wire interventions in the sense how much we can do with better planning before we have to upgrade the grid, which is a problem, but also long-term optimization, because that's what we try to do here. We want to improve the buildings overall. So when the buildings are renovated, their demand changes, but their system changes. It's not a static node. So that's how we need to look at it. And finally, so what I showed before was primarily focused on electricity. I want to briefly mention something about district heating, because in the Netherlands and also other countries it's becoming a bigger issue. So in the Netherlands, we have the goal to have half electrified with heat pump and half with district heating of the building stock. So then the question that rises is, are the buildings ready to have low temperature district heating? Because district heating is effective when we can lower the temperature. So we developed a methodology to do that, to first identify if that's possible. We call them low temperature ready, and then identify what renovation options are possible. So the first thing is to simulate an existing building, and very briefly, what we see here, so that's the high situation with high temperature heating. If we do nothing and we just go to medium temperature, we decrease the demand a bit, but we increase a little bit the hours that is too cold. If we go to low temperature, which is this part, which means 55 degrees or lower, then we can really see that we have a lot of discomfort. So in that case, that building is not low temperature ready. And then we get into what renovation options are there, and we have defined the different levels. And then this is, for example, for that building, the level that we need to renovate to be able to, so that's the minimum level, which includes insulation, replacement, and also increase of having low temperature radiators. But of course, if you want to go, you can to a higher level, it's also possible. But at least that's the minimum level. So we have to see, like in this graph, like myself and I think a lot of us here are coming from the perspective of the building and the facade design, so we are more here. But if we look at the bigger system, this can influence our decisions. At the same time, what is possible to do in the buildings can also influence the overall energy planning. So to conclude, to upgrade the existing building, I really see it as a pathway towards decarbonization. So it's not something separate, it's really integrated. We are able to upgrade the existing building to a very good level, zero energy, zero operational carbon. But it's important to have affordable and future-proof solutions, so to know how we can still operate this in the future, and also how they are able to be connected with more sustainable energy supply, as the example of the low-temperature district heating. Life cycle is important. I already mentioned a few things about how circularity can be integrated. And then strategic renovation planning should be really a part of the short and long-term optimization planning of our decarbonization. Thank you.
Thank you, Talia. Thank you very much for the interesting presentation and the interesting strategies. And now Thank you. Okay, now I want to welcome the next speaker, Rosa Romano from the University of Studies Florence. She's an associate professor, and she will talk about regenerative envelope to transform the city into a resilient and biodiverse ecosystem. Thank you.
Thanks so much, first of all. Okay. Okay, she work, I hope, yeah. Thanks so much to have the opportunity. Sorry, I have to move. Okay, it's good? Okay, perfect. Thanks so much to have the opportunity to be here today to talk about some results of my research that I have developed in the last year with my research team of the University of Florence about, to try to develop innovative technology facade system that are able not only, to decrease the energy consumption of the building during the deep renovation of the building environment, but also, to increase the situation of the urban environment. Because, we try to work not only on the building construction sector, but we try also to work to, find an innovative solution for the urban ecosystem, because our city is part of a big framework where it's necessary, to improve also the outdoor comfort condition and the situation for the people that live outside of the building. In this way, maybe we can try also to improve the comfort condition inside of our building and decrease also, the energy consumption, in particular in Mediterranean area during the summer months. So, with this objective, we try to develop some research related to three main pillars that you can see in this slide that are, focused on the humanity necessity, and we try to move to an approach that is more species-specific, where, we have not so the anthropogenic approach, but also an approach that considers the vegetation and the other organic system that live in our urban space. And the second pillar that we try to integrate in our research approach is the pillar related to the environment, clearly, but with a special focus on regenerative design. And finally, we try also to develop some innovative technological solution for the building envelope to answer to the question related to the topic of Industry 5.0 and clearly to related also to the topic of circular economy. I try to move on, so, no. Oh, I closed the video. Okay, no, we are here. Here you can see, the big framework that we have created in order to develop this innovative typology envelope, in particular realized with the additive manufacturing. We starting clearly with the analysis of the state of the art of the components that are realized around Europe using 3D stamp, and that can also are designed in order to integrate vegetation and to improve the biological components of the building environment. After we try to start to design this typology of envelope, and we create a connection also with the Delft University university, in particular with the Lama laboratory that is in charge of the colleague Michela Turin. And finally, we have received some financing from the national government, in particular from the Tuscany region, to develop some prototype of innovative facade realized with additive manufacturing and developed to integrate plant. Today, I want to show you some result of one of these research. We have in charge in this moment two research, reversing research and urban bloomer research. In parallel, we have also developed a PhD research in the framework of the restorative envelope realized with additive manufacturing. But today, I want to show you one of the results linked to this urban bloomers research that was co-financed from my university, the University of Florence. Is a public engagement research, and this is very strange because we try, to develop innovative design and innovative component, but working with the users of our pilot project, that is in this case are two schools in Florence, where we are called to realize two prototypes of wall system realized with additive manufacturing. And here you can see the consortium that work with us in order to achieve this objective. Is a little bit interesting consortium because are part of the consortium clearly public administration that provide us the pilot, the municipality of Florence and the Tuscany region, but also two small medium enterprise, Canstrapper and H2020 Direct. There are two enterprises that working with 3D stamp system, using two different typology of 3D stamp system and two different typology of material. In the case of Canstrapper, we work with plastic polymer materials. In the case of H2020 Direct, we work with clay. Today, I show you some, prototype realized with clay. And it's very interesting because also in this case, for us, the users are not only the human, users, but also the plant users. So for this region, this research was developed also with the connection with other departments and scientific area, in particular with the area of biology and the area of Department of Agricultural, Food and Forestry Science and Technologies of my university. And finally, also in this case, with the connection of the PhD involved in the research, we can realize the first prototype in clay in the Lama laboratory in Delft. Here you can see clearly the first phase of the urban bloomer research. We try, to analyze at least 50 case studies that we have collected in a digital database that we hope to put online the next month in order to analyze, which typology of additive manufacturing today are used to produce also facade component. Which is their impact also from the point of view of the environmental, condition, because, additive manufacturing have need electricity. It's not clear how many times we have needed to produce the component and which typology of, material it's possible to use during the process. So we try to analyze this aspect, and a first result of our research is this database and some publication linked to this first phase. After we move to the modeling process because we want the baseline of our research is move on to the concept of the green living facade, because we have many examples of green living facade that it's possible to integrate in an external layer of a building envelope. But we have also problem to maintain the vegetation in this typology of technology. So to solve this problem, our idea was to develop geometric framework of, external shade of the building, designed to guarantee the survival life of the vegetation that we can integrate in the living facade system. For this, with this objective, we have created a matrix of geometric, solution that it's possible to use to integrate different typology of vegetation and plants. Here you can see in the first line the geometric solution that are more useful to integrate plants that have need space for their radical apparatus. In the second line you can see rugged surface that are more useful to integrate plant like Cimballaria muralis or rosmarino, other typology of plant that I have not need so more soil to grow. And finally, you can see a geometric solution inspired from cellular structure, where it's possible to put climbing vegetation. Clearly, our another objective is create an environment for the plant, but also to create an envelope that is able to decrease the negative effect of the urban heat island, in particular in the Mediterranean area. So for this region, we try also to modeling a shape that are able to guarantee a correct, adaptivity of the envelope inside of the urban space. Clearly, our approach is a multi-species design approach where the plant as primary, user and direct users of our architectural product. And starting from this, theoretical point of view, we have developed the design phase, identify the users, in this case the users are the plant. After we try also to collect data in order to guarantee the performance, mechanical but also thermal performance to our envelope. And in the fourth step, we start with the modeling of the facade with the software that can be linked with the 3D printing stamp. And finally, you try to develop the prototype. From the point of view of the vegetation, we have selected some typology of plant that can be, linked with two main groups: the plant that are available in the urban environment and the plant that is possible to find in the market. And we create with our colleague of biology also a matrix to study the geometrical and so the technical performance of the typology of plant that we have to try to integrate in our world. After, we try also to focus our attention in the environmental performance related to the thermal needs, the water needs, the sun exposure, the nutrients needs. And finally, also we try to analyze the plant from the point of view of the interaction with the biosphere and the atmosphere, because in our research is involved also Stefano Mancuso that try to study the vegetation from this neurological point of view. So at the end, we have selected the Cimballaria muralis with stress-resistant plant that we decided to integrate in our prototype of regenerative envelope, because the Cimballaria muralis is a plant that is very spread in the urban context of the old city of the European country, in particular in South Europe. It's very stress-resistant, can grow in a hot and cool environment. And as you can see in this slide, this typology of plant have not need so more soil to grow. So we decide to integrate this plant. As I told before, we study, the characteristics of the plant from the point of view of the root growth direction, leaf growth direction, and clearly respect of also the reactivity with the sun in order to decide which is the better orientation where we can integrate our envelope with this typology of plant. And we have also decided which typology of geometry modeling in order to integrate the Cimballaria muralis, and our decide slide is to work with a robust surface, with an horizontal development that integrated with some little space where it's possible to put soil and after plant. And here you can see the first phase of our design. You know, we want to work with 3D stamp machine. So it's very important to develop a model of the components with software like rhinoceros and grasshopper, but after this first modellation, it's necessary also to develop a slicing process in order to guarantee that the machine can realize what we want. So in this slide, you can see the modellation phase of our components. After we start with the realization, now I don't know, the video don't work, but it's not important. In any case, you can see the first prototype realized in Delft in the Lama laboratory with their 3D stamp print. And in this phase, we have to test the diameter of the extruder component of the 3D printing machine, because it's very important to control the definition of the shape of the machine. And in this slide, you can see some picture from the post-printing process. Clearly, after the realization with the 3D printing stamp, we have need, to pass to a drying phase. After this phase, we have a first quality control of the model from the point of view of the geometric and mechanical performance of the component. And after this quality control, we can move to the firing and in a kiln at 1,200 degrees Celsius. And finally, we have our component realized with clay. And after this phase, we're starting with the analysis, the validation phase related to the integration of the vegetation. And in this last picture, you can see, the phase that was developed in the plant physiological laboratory of the University of Florence in order to put plants of Cymbalia muralis, but also seeds, and to analyze if the plants survive in our components. And I can finish with this picture. The plants survive, so the next step is I hope to realize the prototype of a wall that can be integrated in a school in Florence, and after put sensor and analyze what's happened in the real environment with this typology of shape that can be integrated in normal ventilated facade system. Thanks so much.
Thank you. Thank you very much, Rosa. Very interesting presentation and, let's say, inspiring process in integrating nature in our buildings. Next speaker will be connected online, I guess, or is already connected online. Welcome, Carola Tardo from University of Catania, and also co-founder of We Design Studio, a spin-off of University of Catania. So perfectly integrated in this session, so research to practice. So you will have an interesting presentation on joining energy and seismic features for a building system. The floor is yours, please.
Thank you, thank you. Do you hear me?
Yeah, we can hear you.
Perfect, perfect. So, hi everyone. I'm Carola Tardo, and I'm a researcher of architectural engineering from the Department of Civil Engineering and Architecture of the University of Catania. I thank the organizers and in particular Professor Mazzucchelli for the invitation. I really apologize for not being able to attend in person, so I thank you for the opportunity to deliver my presentation by remote. Today, I will illustrate the main outcomes of a research project that was coordinated by the University of Catania and was aimed at developing and demonstrating novel prefabricated facade solutions for both seismic and energy renovation. The project was conceived from the evidence of the current conditions of the existing buildings in the most European earthquake-prone countries. In these countries, such as Italy, Turkey, Romania, Greece, and all the Balkan regions, around 65% of the building stock is not only highly energy intensive, but also highly earthquake prone. And this because it was built before the enforcement of the most recent and effective energy and seismic policy.
We cannot hear you anymore. No, I don't know if the problem is on your side or on our side, or both sides. Can you hear us? Yeah, but we cannot hear you. I don't know if you can try without a headset or no, doesn't work.
Okay, now.
Yeah, it works. Please go on.
Okay. So, in Italy, for example, it is estimated that approximately 1 in 2 Italians lives in buildings which require both seismic and energy renovation. Unfortunately, damaging earthquakes can occur at any time. Just to give you some figure, according to the International Disaster Database, only in the last 50 years, only in the countries indicated in the map, earthquakes have caused nearly 90,000 deaths, over 1.6 million homeless, around 25.5 million people affected, and over 270 billion economic losses. So these data show that in these countries there is a strong need of renovation actions that synergically integrate both energy efficient and anti-seismic interventions. However, today the implementation of integrated retrofit strategies is mainly hindered by the limit of the main traditional seismic retrofit techniques, which often require a long time for implementation, the relocation of the occupants during works, intensive demolition and reconstruction works, and high cost. So, to overcome these limitations, as part of a European research project called eSafe, we've developed novel integrated seismic and energy retrofit technologies, which intend to also reduce time and cost for implementation, reduce the disturbance to the users, and reduce the building's environmental impact. The same project has been completed last month and has involved a multidisciplinary research team that included 12 partners from 8 different European countries, some of them highly earthquake prone. The safe solutions are based on the use of prefabricated technologies which are applicable in buildings with reinforced concrete frame structure. One of the solutions is shown in this slide. The solution consists of cladding the facade of the building with prefabricated wooden panels to create a new building envelope that is both seismically resistant and energy efficient. Are combined 2 types of panels, which are called ECLT and A-panel technologies. The ECLT are structural and insulating panels which are applied to the blind walls of the building. These panels are basically made of cross-laminated timber and are fixed to the existing structure through special steel connection which act as energy dissipation devices. These panels allow to increase both the seismic and dissipative capacity of the existing structure thanks to the high mechanical properties of the CLT and the additional energy dissipation source. In this way, in case of earthquake, these panels reduce the drift demand of the structure, thus limiting its damage and avoiding its collapse. In this slide, you can see the dissipative device, which is combined with the CLT panel. It is a friction damper made of steel profiles in plates, which are properly assembled on site. In case of earthquake, as shown in the video, this component can slide against each other as a result of the interstory drift of the RC frame structure. So the seismic energy is dissipated by exploiting the friction which is caused by the mutual sliding of the steel surfaces. The ECLT panels were conceived to be combined with another type of wooden panel which has not structural role but provide only thermal insulation. These panels are applied to the window walls of the building and can integrate new high-performing windows in replacement of the existing ones. Both panels were designed to be totally prefabricated off-site. So they integrate a stratigraphy that includes a layer of thermal and acoustic insulation material, a weatherproof membrane, and the cladding layer. Overall, any type of cladding material are suitable for these panels. The main difference between the two panels is in the main structure. The structural ECLT panel is made of cross-laminated timber, while the other one is made just of a wooden frame. If the ECLT technology is not applicable or is not sufficient to achieve proper level of seismic improvement, such as in building with large windows, another retrofit solution provides to clad the facade of the building with all insulating panel and combining this panel with the three-dimensional steel chassis, which are called E-Exos technology. These chassis were designed so that in case of earthquake, they can evenly distribute the interstory drift along the height of the building to avoid mechanism of substory collapse and also to reduce the drift demand of the existing structure. The same technologies have been demonstrated in 3 pilot buildings located in seismic countries with different climatic conditions. The first pilot is a residential building located in the city of Catania in Sicily. This is the former state of the building before renovation. In this pilot building were applied the ECLT and E-panel technologies, in particular to validate the energy performance and construction feasibility, while the seismic performance was validated only at a theoretical level. This because, unfortunately, the renovation project was downsized since economic and technical issues. During the project, indeed, local structural issues in the stairwell of the building have required traditional reinforcement techniques that could not be covered by the project fund due to the high cost increases in the building market in the last years in Italy. To install the panels were used 3 workers and a mobile crane. As you can see, the panel did not integrate the cladding layer, but this only for the choice of the contractor. The cladding layer has been then applied on site. On the right, you can see the state of the building after renovation. As cladding layer of the panels were used metal cladding on the short front and plaster on the long front. This pilot building is today also one of the Energiesprong pilots in Italy. The other two pilot buildings are located in Romania. In these buildings was carried out only the project of the retrofit interventions, which provide the use of the e-panels in combination with the steel chassis axis. As shown in these images, in both buildings, the steel chassis have been designed to also serve as architectural element and, if required, to support new balconies. So, what are the advantages of these technologies? The safe solutions are quick, sustainable, and low invasive for the users, thanks to the high level of prefabrication and the application from the building outside. They are also designed to be highly replicable and customizable. At energy level, the panels allow to reduce the building energy demand by over 60%, while at seismic level, they allow to reduce the seismic demand of the structure, contributing to reduce the interstory drift of the structure up to 15%. The main target buildings for their application are buildings with reinforced concrete frame structure and with no more than 6 stories. So they are not suitable for net building or for high buildings where the maximum story drift in case of earthquake would be significant and would not be able to be compensated by the structural capacity of these technologies. Furthermore, since the e-safe technologies intend to modify the global seismic behavior of the building structure, any local structural criticalities in the existing building, such as in the pilot building in Catania, need to be solved preliminarily before their application. In conclusion, the ambition of the SAFE project has been to contribute to the development of technological solutions that make our buildings and cities less energy intensive and safer. To achieve this, it is essential that the SAFE solutions are disseminated, appreciated, and applied as much as possible. So, to foster effective market uptake, Unicity has already established a spin-off company called We Design Studio, which offers consulting and design services for retrofit intervention based on the use of the e-safe technologies. I have concluded my speech. Thank you so much for your attention. Here are all the contact details for any further information. Thank you so much.
Thank you very much, Carola, for your presentation. I don't know if you are still there. Okay. Thank you very much.
Yes, I am.
It was really nice despite the connection problems, and I also saw some people from the public taking pictures, so they were also really interested. The next speaker is Miren Juaristi from Eurac Research. She is an expert in innovative facades, and today she will talk about adaptive building facades.
Thank you so much. Thank you for this nice introduction, and thank you for the opportunity of having this amazing space to share what we are doing in TIRAF project. We are developing an innovative facade concept that we hope will help to transform our building stock into adaptive and future-proof one. So the benchmark approach that we have seen also these days to make the building stock energy efficient and comfortable is to highly insulate it, make it airtight, avoid thermal breaches, so that we can reduce drastically the energy demand of buildings, mostly focusing in the heating demand. However, we have seen that this approach has also some drawbacks that, as researchers and innovators, we should tackle and propose better optimized systems. Because by insulating so much our buildings, we are, for instance, missing the opportunity that weather conditions offer at some point of the day, at some point of the year. Of course, depending on the climate of the specific building location. Moreover, we are missing the opportunity of using the building envelope, which is the actual, let's say, barrier or frontier between the outdoor and indoor environments, as the physical space that acts as a modulator. Instead of that, we are fooling our buildings with HVAC systems that occupy space in our household. And we heard yesterday how important it is to have a space because it's really, really expensive right now in the market. So let's think about removing, reducing this space and bringing back to the envelope this role of modulating. And finally, we have here also this morning, we are facing a climate change and we are having more and more cooling loads in our buildings. And what we are doing with them is just putting this blanket. It's a term that we also hear this morning. So what we should instead do is to shift from this exclusive approach of the building envelope that acts as a barrier to become it a selective modulator following an adaptive approach. Use this physical barrier to decide when we want to bring the heat from the outdoor to the indoor or expulse it, or when we want to actually protect from aggressive and unwanted weather loads. So what we are proposing with CIRAF technology is to have kind of different closes to the building depending on which are the conditions and user needs. So basically, we are controlling, first of all, the heat loads that we get with radiation. So think of a t-shirt, right? Think the difference when you are bringing a dark t-shirt, a clear t-shirt, and you have the sun radiation hitting you. So what we do with our envelope is to let the solar radiation hit this dark t-shirt when this is suitable, and to protect with a white one when this is unwanted, for instance, in summer conditions. Then let's talk about insulating the building, right? We have an active insulation system so that when it's off, it acts as a regular insulation. However, when we want to bring the heat to the indoor of the building or to get out of it, we can activate it and act as a dissipator. And finally, we hear this morning the role of ventilated facades, right? So thanks that we have this kinetic cladding that you will see in the next slide, which help us to have the control of the solar radiation, we can also use that to modulate the convective losses that we have in the air cavity. So we control also the convections that occurs in the ventilated cavity that we have behind this kinetic cladding. And this is the system. You are looking at a prototype. Okay, this is the level of maturity that we have, so don't pay too much attention in these sensors there. But basically what we have, it's a kinetic cladding. This is the one that changes the color of the surface that it's in contact with the active insulation layer. The active insulation layer, which is basically, we have some channels milled in these insulation materials where the air can flow when we want the heat to go through our opaque part of the building envelope. And as you can imagine, between the kinetic cladding and the surface of the active insulation, we have this cavity, ventilated cavity, that we can control its opening degree to promote or minimize the heat losses by convection. All this works with automated logic, control logic, so that we know when we need the clear t-shirt or when we need to put the jumper, let's say, or the blanket to our building. It's a concept that, for those that have done some research in adaptive facades, I have some colleagues here. This is a field that it's been there for many years. we know that can bring actual reductions compared to the completely insulated building. So in this graph, you can see the impact that we would have in different climates. Of course, the benefits are different. The climate plays a big role in these adaptive facades. And you can see in the left part of each climate, a typical building, so with the average insulation levels. Then we have a compliant building, so based on the current regulations. Then gold building would be the ones that are highly insulated, the benchmark approach that I mentioned before. And finally, CIRAF. You can see that in warmer climates, it's more promising because it reduces a lot the cooling demand. And in heating dominant climates, we need to have some solar heat gains. So this means that, for instance, in Stockholm, where the heating demand period is also pretty dark period, it's not a technology that would work. Some disclaimers: these are preliminary building simulation results. We should update them with the results we got in the lab with the actual adaptation range. And also, these were results that we got with weather files that were the average one, the ones that we all use and don't even represent anymore the current climate. So the reductions you see in the cooling, we can expect to be much more, and I hope to have these results very soon to show in the next conferences and scientific papers. I would also like to stress the fact that we could even eliminate mechanical cooling, of course, depending on which climates. Again, here, these are with current climate files. So you can see on the left what happens with the static insulation, what happens if we just implement the kinetic cladding, so the change of color, what happens when you have active insulation, and what happens when you have the full system installed, which demonstrates that in those orientations where you have solar heat gains directly hitting your facade, this system, the complete configuration, actually makes sense. So I think that it's important at this point to move from research concepts that look only to the building physics to have a clear picture of how this technology would be implemented in a building. And that's why in this European Innovation Council funded project, from the beginning we had a very clear vision, not only on the features that I just explained you, but also how this should look like in a product that can be actually implemented in the market. And I think that we are in a perfect context here because we saw so many things that are compatible with this technology, and that by joining the forces, we can really do this transformation for adaptive, future-proof assets. It needs to be a facade system that is delivered as a turnkey product, so that we manufacture off-site, so that the complexities of having this kinetic cladding, the sensors we need to understand when we need to shift from one close to the other, it's dealt in factory, in a controlled environment, so that when we arrive to the building, as we saw in so many nice videos these days, it's a prefabricated panel that can be installed. Another two key features that our technology has is related to the material level. We hear today how it's important it is to work at all the levels when we are looking at a product that has the lowest environmental impacts possible. In this case, in our consortium, we have two startups, or one of them can already be considered a small company, that bring us to key materials, which are, on the one hand, a bio-based material, the biopolyurethane, which is an insulation material that its fabrication method is compatible with having these surface channels that I showed you in an industrialized ways. And then smart materials, we have a shape memory alloy that acts as the actuator of the kinetic cladding to do it silent and with the less energy use possible for moving the kinetic cladding as needed. It's an intelligent facade. It involves building automation because there is a control logic, and this means that has a potential to be also connect it to other building automation components, adaptive to be optimized to every moment of the day and every moment of the future years. So it can provide the best performance also in the future. And I think it's very important that we ensure that this technology can be integrated in different kind of architectures so that there is an architect-led aesthetic decision on how this technology looks like, providing them the voice on how the kinetic cladding should be done. And finally, we hear a lot about business models these days. And one thing that it's clear here is that it's an advanced facade that it's kind of doing what the HVAC system does right now for the building. So we need to expect some maintenance, and this means that there is a need to be a company there to provide that service. So it cannot be that the company sells a turnkey product, installs, and forgets about it. So we also need a shift in business models to make this technology suitable for the market, and we are working on it. So the good news is that this solution is also applicable for buildings that are already there with this configuration I am showing you in the screen. And the important thing is that it's not fully glass because it's an opaque facade, right? This is how a building with CRAF could look like. So it's an aesthetic that it's already there, but we are not exploiting what we could do with that look of the buildings. And yeah, very briefly, some results that we got so far. So we built the first prototypes and tested in our laboratories at Eurac Research. So here you can see the adaptation range that we got. So we can shift from an insulation of 18 centimeters to behave as if it was 3 centimeters. You can see the facilities where we perform the test of the active insulation system alone. And here the adaptation range with the full system, with the kinetic cladding closed and open. And you can see how the adaptation range is even bigger. So the full system together makes sense. I am running out of time, so I hope my messages here were clear. I just want to say that right now we have a proof of concept. This concept works. We test it in our labs, and we are starting to do the other kind of tests, fire tests, for instance. And in the close future, we are planning now the implementation in pilot buildings. Also, Rosa said this is their next step, right? So also for us, so we are looking for that pilot building, for that investor that wants to go for this product. So if there is someone here in the audience that is interested in being part of this journey, please contact me. Thank you.
Yeah, thank you very much. Thank you, Miren. Quite insightful presentation, and let's see what will happen in the next future. Move to another colleague at Eurac, Diego Tamburini, researcher at Eurac and expert in prefabricated facade, and with some, let's say, demonstration cases he followed. So let's see what happened when we move from a concept to the reality, so the application of the concept on real buildings. So, Diego, the floor is yours, please.
Thank you, and good morning, everyone. Maybe some of you participated yesterday in the first day, so I will repeat some results of the INFINITE project, and you already know the project. So the Horizon 2020 INFINITE project is funded from the European Commission for 8 million euros, and 20 partners with different partners from university, research centers, industry, startups, and real estates. The focus of the project was to industrialize the retrofit of existing buildings through prefabricated timber-based panels for facade and roof with different technologies. We have some technologies for the cladding, for the facade, so to have also active cladding in the facade of the buildings, such as the BIPV and BEAST, so photovoltaic and solar thermal, building integrated solar thermal, and some technologies for the indoor comfort of the apartments, such as the ventilation machine from Vortice, presented yesterday, and some technologies studied for the smart windows. We had 3 demonstration buildings, France, Slovenia, and Italy. For France, we could implemented only the BIPV technologies. For the Slovenian, we had several technologies, and then we could add a new floor in the building. And then for the Italian demo building, we had the BIPV solar thermal ventilation kit and the smart windows. The Italian demo were two twin buildings with 4 apartments per building. The year of construction is 1978-1979, with a concrete frame structure and brick infill walls. The energy system were independent heating system and for the heating and the domestic hot water for each apartment. You can see some picture of the existing buildings, and we had several audits for the project. So some for the consumption of the energy consumption of the apartments. Some energy audits, thermographies, and studying also the wall stratigraphy to identify also the thermal breach of the building. Some structural audits also for seismic reasons, and social audits to understand also and identify the needs of the tenants of the building. One of the most important audits was the geometry audit with some surveys with drones and laser scanners to create a point cloud and the beam model with the help of one team. And we could understand also the differences of the measurements from the point cloud and the traditional survey from Fanti Legnami, the company who produced the facade. We had several global and detailed energy simulation and modeling. So some detailed simulation for the ventilation machine from Vortice to understand the risk of condensation or air leakage of the air ducts of Vortice, and global simulation to create the energy model with transits with the Eurac colleagues, and analysis for the solar radiation potential to identify the portion of the facade where we could install the BIPV or the solar thermal, and to have more production and to reach the NZ targets. So the system concept, we had an industrialized envelope with Fanti Legnami. We had a new heat pump to serve the heating system and the domestic heat water. So to serve also the new ventilation machines, we had 2 units per apartment. Then the BIPV in the facade, for the common loads and the heat pump, and smart windows integrated directly in the new facade. Okay, we had to prepare the building side for the installation of the prefabricated facade, so we had to destroy the old roof and old balconies because were deteriorated, and the old roof for loads reasons and for seismic reasons to install the new facade. So we can see the concept design with the integration of the different technologies. Yesterday you could see also the model from Fanti Legnami. The new of this project is to install a global integration also of the air ducts from Vortice in the panels, prefabricated panels of Fanti. So we can see here the integration of the ventilation unit and the air ducts in the facade of Fanti. And the challenge was also the installation between panels, not only for the joints and the air and water tightness, but also to connect many air ducts between panels. We can see here some of the tests in the laboratories of Eurac, indoor test and outdoor test for the performance of the ventilation unit of Vortice. With the two integration under the window and in the parapet for the balcony. These are some mock-ups from Rubner Holzbau that we installed in the Facade System Interaction Lab of Eurac Research. This is the concept of the BIPV. So we installed in the roof and in the east and west facade of the building of Grevin Chianti. Some of the tests in the Flexi Lab outdoor laboratories of Eurac, testing the performance of different BIPV panels with different colors and textures. And the integration also of the solar thermal. In the concept, we had the integration in the south facade of the solar thermal, but for technical issues, we could install only the passive cladding with a new fixing system. These are the tests also in the Flexi Lab of Eurac. And the other technologies were the smart windows with electrochromic, plasmachromic, and the integration of lamellas integrated inside in the double glassing with a NextSense sensor to control the radiation and managing the optimal position of the shading system. We installed this system with Pellini in the demonstration building, Italian demonstration building. We had a building management system, some tools connected with the BIM platform, one team BIM platform, to identify the energy impact of the project and to analyze also life cycle cost, life cycle assessment. So we can see some picture you have already seen yesterday maybe of the production with the air ducts inside the panels. The production of the roof, the off-site production in the Fanti Legnami factory, and the installation of the substructure for the new claddings and the new technologies such as the BIPV and the solar thermal. Everything in the factory, in the facilities of the Fanti Legnami. It's a picture of the transport, the preparation of the building site with the demolition of the roof, the existing roof, and the installation of the prefabricated roof with the Fanti panels. And in the picture on the left, you can see the preparation of the existing facade with the anchoring system for the new facade and some holes to install the inlets and outlets for the air ducts for vortice system. The installation of the technologies, so with the ventilation unit of vortice, in the south facade the solar thermal, and in the east and west facade, in the corners we can see the BIPV from SunAge. Every panel with the red oxide color for architectural aesthetical reason from the architectural studio. And the final result. For the Slovenian demo, I have a few seconds. So we had a new floor, and the important thing for this demonstration building is that with the new apartments they built in the new floor, they sold this apartment, and they could finance also a big portion of the renovation of the existing building. So it could be a new business model also for this kind of intervention. Some picture of the installation for the facade for the existing building and the construction of the new floor, and the technologies. So we can see the facade with the BIPV cladding of SunAge and the green technology. Thank you.
Thank you.
So the time were for the Italian demo 3 weeks for the installation of facades and the roof, but I was present in the installation of the east facade, and we have a time lapse, and they finished the east facade in 3 hours. So it's a good result.
Thank you. Thank you very much. It was really engaging. Now the floor goes to Alessandro Zanini. He is an architect with international experience who's now working at EDERA here in Milan. And you have the floor.
Yeah, thank you everybody. Thank you for being still awake. It's very late. We hope to have lunch as soon as possible, but I'll take 10 minutes of your time and then leave the space to Pellini that is here and support us in this session. So I'm here to talk about Reno Tides. Reno Tides is a European project, a live European finance project that aims to support stage massive net zero retrofit with collective buying schemes. So of course it's a very long title. I hope by the end of the session we all can share what it means. It's all based on the process of Energiesprong. So Energiesprong is this, of course, I guess all of you know it. If you have been yesterday for sure, today as well. But it's this open innovation project that focuses on the process. And together with our European partner, we got to the goal of making up to 40,000 retrofits with shorter times, reduction in the cost, NZEB performances, and many other kind of process improvement, including for the Italian case, the anti-seismic improvement, that it's a uniqueness and is quite relevant. As you know, it is decarbonized, so it's in line with the goal 2030 for European decarbonization. It is safe because off-site panels production in the factory allows for reduction of work in height, and so safe for the construction worker and safe for the people living, as improving the anti-seismic performance. It is scalable. Oops. It is scalable because the industrialization allows us to scale and improve the masses and the amounts, and hopefully it's desirable if we are good to make a good product. So hopefully, and sometimes a problem emerge. So the problem of the cost and the financing. The goal of the project is to support the next wave of off-site retrofits. So it is a project that is still ongoing. So today I don't have any answer yet, but we have a lot of questions and a lot of points that I think can be interesting to throw, like seeds, and maybe some of you, I see a lot of students, can pick up this reasoning and maybe bring it forward with us. So we need to solve these economic and financial problems. Of course, there is economic financial context that doesn't help. The rising of material cost, the aging labor force, and the unpredictable interest rate create an environment where financing this project that are particularly integrated and complex can be hard. So our solution, or possible solution, is why don't we think with time? So why don't we try to stage this retrofit? Stage means doing it step by step, and apply these collective buying schemes by putting big groups of buyers together to bring down the cost. So that's the logic behind Reno Tides, this project that we are collaborating on. So as I was saying, by stages, it means that maybe throughout 5-10 years, we can do the facade first, and then do the roof insulation, and then maybe work on the heat pump and the system, and that would allow to break down the cost through time and to do this intervention whenever it's possible, so whenever it's realistic and whenever the owners have the resources to do it. And the second approach that we try to push is for collective buying schemes. So why don't we put big groups of housing together with similar typologies and then do these same stages maybe in steps, but all together. So hopefully, the goal is that this clustering enabled for retrofit tides, that's where the names come from, and bringing economy of scale, this could bring down cost. So this is the overall goal, hopefully. So we're working on multiple levels, like the whole Energiesprong movement is not only technical, it's not only social, it's not only financial, it's not only contracts, but it needs to be all of this together. So this is one of the first outcomes that we did. So a diagnosis tool for self-retrofit. So hopefully, housing association can pick it up, and it's a very simple Excel, and take in consideration the context, the parcel, and the building itself. Maybe they can understand themselves if the building is suitable for an off-site renovation. And by doing this, the goal is that we can do a first feasibility filter to speed up the whole process. So another strategic and technical solution was to identify the typologies. So we heard a lot about clusterization these days, and we are doing this at a European level. So we're trying to understand what are the typologies geometrically, of course, in terms of system status, and in terms of the decarbonization potential for applying these strategies so that we can get some results that are maybe useful for the whole European households. The idea, of course, is to get to a common working platform. Another strategy that we identify is what are the steps that we need to do. So maybe we can start with the envelope, maybe just the vertical, maybe the horizontal, maybe the windows, maybe not, and then maybe we can go to PV panels or maybe change the heating generator, so the system. So these are just some scenarios that we are indagating, and we hope that some of you can collaborate into this, because we think that this step strategy might be a solution, and of course we are pushing them to test these solutions. Another strategy that we saw, luckily, many times before, yesterday and today, is what if we try to finance this intervention with rooftop expansion? So by building another apartment and maybe selling it out or renting to a higher rate, then this can be helpful in financing the whole renovation. And what if we grow the quality of the apartments by adding balconies or external space that are so needed? Everybody wants a house with a balcony. I do. And then, of course, we are studying the feasibility, the technical feasibility, the regulatory constraints, and of course the potential revenue stream, as I was saying, to help finance the whole renovation. Of course, as I was saying, it's not only technical, but there are some economical, financial strategy that we're trying to implement and study. So the EU taxonomy maybe can help us to get lower rates for this intervention, and if our intervention can be compliant to that, that can of course help to finance the whole strategy. And what if we apply some roof or facade as a service? This is a concept that is already applied for solar panels or system, where you don't sell the product, but you sell the service that the solar panel can bring, so the electricity production. What if we try to explore the same strategy for a roof or facade? Of course, it's a complex, but maybe it's an idea, and we're trying to investigate that. And of course, we are working with contracts, as all these steps maybe need to be kept track. So what if we do a building passport for the building? Of course, there is a European regulation that requires that, but that can be helpful in supporting the step renovation. So as I was saying, this is an ongoing project, so we don't have results yet, but I hope that we gave you some hints, some idea to think about it. When we will have results, hopefully as soon as possible, we will come with some training on the specific issues. These are pictures of the consortium meeting we did last week or 2 weeks ago in Rotterdam, where we discuss all together with the partner and we visit some construction sites. That's always a good insight to go and see the reality of things. And of course, this is a team effort. So here you see a lot of logos, a lot of companies from 7 different European countries. But I think the key point of this collaboration is that we can one day discuss within a market development team, and then discuss and confront with university, and then go to the housing association that can prove or disprove our point. And this is like an effective and interesting process. Of course, this is, as I said, is an ongoing process. So if you're interested, you want to follow our updates, get in touch and be part of this. Thank you.
Thank you. Thank you very much. Yes, is Giovanni there? You can, and thank you very much. So it was a very good example of practices of, let's say, implementation of renovation and renovation through modular systems. So we are approaching the end of the session with the last presentation by Pellini. Before, a couple of messages for the speakers of these sessions and the previous sessions. If you can stay for a while, we can take a common picture all together at the end before lunch. So please stay here in the room. And the second is related to the next EFN conference. Will be in Delft next year, 2nd of June. So still in the organizational phase, but already fixed the date. So save the date, 2nd of June in Delft. And yeah, we are ready for the last presentation by Giovanni Gennaro, Pellini. So the floor is yours. I thank you for sponsor the session.
Grazie Roberto. Allora, buongiorno a tutti, sono Giovanni Gennaro di Pellini SPA e noi siamo leader nel settore delle schermature solari da oltre 50 anni, sia in ambito residenziale ma anche dal punto di vista dei cantieristica, ma anche forniamo anche tende di lusso negli yacht. Infatti abbiamo 3 diversi core business: il primo le screen line di cui oggi vi parlerò, presenterò alcuni prodotti, e poi abbiamo anche, produciamo tende tecniche da interno e tende per yacht e navi di lusso. La screen line è la tenda integrata dentro il vetro, è stato la prima tenda che abbiamo brevettato negli anni 90, che consiste appunto nell'integrazione della tenda in un doppio o triplo vetro. E abbiamo 3 diverse soluzioni di schermatura solari e 6 diverse movimentazioni che appunto danno una varietà di possibilità nell'ambito degli edifici, sia dal punto di vista di edifici pubblici come scuole, uffici, ospedali, ma anche nel residenziale. Oggi vorrò parlare di un sistema motorizzato, che è il V-Smart, che appunto abbiamo utilizzato anche nel demo case di Infinite, che consiste appunto in un modulo batteria che permette la movimentazione e il controllo delle tende integrate. Il cuore è il modulo batteria, che quindi ha un pro, nel senso che dal punto di vista della renovation non ha bisogno di opere murarie per il rinnovamento tecnologico, ma basta solamente cambiare il serramento e possiamo appunto aumentare la performance dell'edificio, perché appunto avendo una schermatura integrata nel vetro aumentiamo la performance energetica dal punto di vista sia del comfort visivo, perché appunto andiamo a modificare, a modulare la quantità di luce naturale entrante negli ambienti interni, ma dall'altro lato andiamo a ridurre il fattore solare e quindi i consumi energetici. Inoltre è possibile anche integrarlo nel nostro sistema domotico, il Wise Hub, e quindi poter andare a ottenere, a implementare anche delle regolazioni più o meno sviluppate per appunto ottenere il giusto bilancio tra risparmio energetico e comfort visivo. Adesso vi parlerò anche di nuovi prodotti, alcuni sono già stati brevettati, altri abbiamo già presentato domanda di brevetto nell'ambito del miglioramento tecnologico delle nostre screen line. La prima è legata a una richiesta da parte dei nostri designer dal punto di vista estetico. Infatti quando si utilizza un vetro triplo e quindi un vetro selettivo, perché appunto per migliorare da una parte la performance energetica del componente vetrato, dall'altra il selettivo va a influenzare la percezione del colore. Infatti come vedete qui abbiamo una simulazione di come appare un vetro e una lamella grigia dietro un vetro selettivo, quindi ha un'apparenza verde giallognola dovuto appunto al selettivo che va a distorcere la percezione del colore. Quindi noi siamo andati a lavorare di reverse engineering e quindi andare a trovare uno speciale pigmento che andasse appunto a neutralizzare questa distorsione cromatica. Il risultato è una tenda, la vedete qui a sinistra, una tenda dall'aspetto neutrale in confronto a una tenda grigia con lo stesso selettivo, un triplo argento 6027, quindi altamente distorcente, e appunto siamo riusciti a ottenere la neutralità, quindi poter accoppiare da un punto di vista sia la parte estetica ma anche dal punto di vista di performance, quindi poter usare in facciata il selettivo. Ogni selettivo ha un modo di distorcere il colore in modo diverso, per cui bisogna fare una sorta di calibrazione ad hoc. Noi abbiamo in house una sorta di simulatore solare che va appunto ci aiuta a capire se dal punto di vista delle simulazioni, quindi dal punto di vista delle coordinate cromatiche della lamella color neutral, riusciamo a ottenere la neutralità, e quindi possiamo fare in house anche dei mock-up utili appunto ai progettisti per appunto verificare in campo, quindi con la composizione di vetro e la schermatura, appunto la neutralità. La seconda tecnologia è la lamella retroriflettente. Nasce dall'esigenza più che altro di performance visiva. Infatti le tende che utilizzano lamelle standard super riflettenti hanno da un lato il vantaggio di poter tramite la riflessione andare appunto a massimizzare la quantità di luce naturale che entra in ambiente interno con il cosiddetto light shelf, dall'altro anche aumenta le performance energetiche, perché appunto con le lamelle altamente riflettenti si ha un basso fattore solare, però dall'altro necessitano di un controllo e quindi un'automazione dedicata, perché appunto c'è un maggior rischio di essere abbagliati, sia dalla parte interna che dalla parte esterna. Per cui abbiamo lavorato su su come trovare un giusto bilanciamento tra performance visiva e energetica, andando a lavorare sul coating. Quindi abbiamo brevettato questo coating retroriflettente che è basato su microsfere di vetro immerse nella vernice della lamella. L'effetto è che va a retroriflettere alla sorgente la luce e quindi il calore incidente in lamella. L'effetto che si ha è una lamella che ha un comportamento, un aspetto matte rispetto alla lamella bianca standard dovuto appunto a queste microsfere di vetro immerse nella vernice, però con l'effetto di ottenere una miglior performance visiva. Non abbiamo glare né dall'interno né dall'esterno. Questo significa che anche col sole in facciata possiamo mantenere le lamelle un po' più aperte e quindi permettere la visione con l'esterno e anche maggior utilizzo di luce naturale per illuminare gli ambienti interni. Dall'altro, tramite la retroriflessione, abbassiamo il fattore solare, quindi migliora la performance energetica e riduce l'abbagliamento dalla facciata esterna. Abbiamo fatto delle misure di caratterizzazione sia dal punto di performance energetica che visiva presso i laboratori di Eurac Research nel contesto del progetto europeo M0I, e vedete che confrontando 3 facciate con la stessa composizione di vetro ma cambiando solo la lamella, quindi una lamella grigia, una lamella bianca e una lamella retroriflettente, vedete che la lamella retroriflettente ha un fattore solare quasi minore del 50% rispetto alla lamella grigia. Invece dal punto di vista della riduzione dell'abbagliamento esterno, qui vedete un time lapse che abbiamo fatto durante una giornata a Bolzano, in cui vedete che la facciata non si accorge di essere irraggiata dal sole, nella retroriflettente, nella bianca invece inizia a illuminarsi, mentre nella grigia è fortemente abbagliante. Finisco con l'ultima tecnologia, che è la Wave, che è una sorta di nuova tecnologia di schermatura solare che è costituita da un microfilm in poliestere che integriamo nel vetrocamera da 22 o 32 mm ed è il frutto di anni di studio, di ricerca, di sviluppo. Pensate che i primi studi relativi alla Wave risalgono a 10 anni fa. È una tecnologia nuova che abbiamo ingegnerizzato anche il processo produttivo nel modo di arrotolare il film sul tubo in modo da permettere il sollevamento costante e autonomo della schermatura solare, migliora la condizione energetica in quanto appunto è un tessuto, un film plastico metallizzato, per cui va a ridurre almeno del 10% il fattore solare del componente vetrato e permette di ottenere il buio, quindi appunto di ottenere blackout nelle stanze. È possibile in diversi colori e finiture per appunto ottenere sia il blackout che l'effetto filtrante, ma anche ad oggi siamo anche in grado di microforarlo, quindi per andare a sostituire, a integrare la possibilità di una schermatura filtrante, come per esempio un tessuto metallizzato, dentro la camera vetrata. Il processo di perforazione è in house, quindi possiamo andare anche ad personalizzare sia il pattern di microforatura che anche il grado di apertura, quindi andare a modificare l'opening factor del solar shading, e quindi va a migliorare sia la performance energetica che visiva. Io ho finito e qui trovate i miei contatti per avere supporti anche lato tecnico. Grazie.
Grazie mille Giovanni, grazie ancora appunto per la sponsorizzazione. Thank you very much. Thank you also for the presentation. Thank you all for being up to the last minute of the session. We are ready for the lunch. Again, for the speakers, if you could come on the stage, we can have this common picture altogether. Thank you all. Thank you also,
Thank you.
Sophia, for sharing with me. Thank you.